What's up everybody? Today's video is a collection of course videos from our Keras Fundamental skill track. In these videos, you'll learn all about how to build neural networks with Keras, how to approach image modeling and convolutional networks with Keras, how to build sequential neural networks, and a lot more. If you enjoyed these videos and you want to actually apply what you learned in these videos right in the browser, check out the link in the description below. And with that, happy learning!
Welcome to this course on deep learning. I'm Miguel, and I'm very excited to be teaching you Keras here on DataCamp. This course will add Keras as a powerful tool to your arsenal. Keras is a high-level deep learning framework. To understand what is meant by that, we can compare it to a lower-level framework, like Theano. Building a neural network in Theano can take many lines of code, and it requires a deep understanding of how they work internally. Building and training this very same network in Keras only takes a few lines of code. Much quicker, right? Keras is an open source deep learning library that enables fast experimentation with neural networks. It runs on top of other frameworks like TensorFlow, Theano, or CNTK, and it was created by French AI researcher François Cholet. So why use Keras instead of other low-level libraries like TensorFlow? Well, with Keras, you can build industry-ready models in no time, with much less code than Theano, as we saw before, and a higher abstraction than that offered by TensorFlow. This allows for quickly and easily checking if a neural network will get your problem solved. In addition, you can build any architecture you can imagine, from simple networks to more complex ones, like Autoencoders, Convolutional, or Recurrent neural networks. Keras models can also be deployed across a wide range of platforms like Android, iOS, web apps, etc. It is the best moment to be learning Keras. Keras is now fully integrated into TensorFlow 2.0, so you can use the best of both worlds as needed and in the same code pipeline. If as you dive into deep learning, you find yourself needing to use low-level features, for instance to have a finer control of how your network applies gradients, you could use TensorFlow and tweak whatever you need. Now that you know better what Keras is and why to use it, perhaps we should discuss when and why to use a neural network in the first place. Neural networks are good feature extractors, since they learn the best way to make sense of unstructured data. Previously, it was the domain expert that had to set rules based on experimentation and heuristics to extract the relevant features of data. Neural networks can learn the best features under combination. They can perform feature engineering themselves, and that's why they are so useful. But what is unstructured data? Unstructured data is data that is not easily put into a table. For instance, sound, videos, images, etc. It is also the type of data where performing feature engineering can be more challenging, and that's why leaving this task to neural networks is a good idea. If you are dealing with unstructured data, you don't need to interpret the results, and your problem can benefit from a known architecture, then you probably should use neural networks. For instance, when classifying images of cats and dogs, images are unstructured data. We don't care as much about why the network knows it is a cat or a dog, and we can benefit from convolutional neural networks, so it is wise to use neural networks. You will learn more about the usefulness of convolutional neural networks later on in the course. Let's start building neural networks. In a nutshell, a neural network is a machine learning algorithm that is fetched with training data for its input layer, to then predict a value at its output layer. Each connection from one neuron to another has an associated weight, W. And each neuron, except the input layer, which just holds the input value, also has an extra weight, and we call this the bias weight, B. During Feedforward, our input gets transformed by weight multiplications and additions at each layer. The output of each neuron can also get transformed by the application of what we call an activation function. Learning in neural networks consists of tuning the weights or parameters to give the desired output. One way of achieving this is by using the famous gradient descent algorithm, and applying weight updates incrementally, by a process known as backpropagation. That was a lot of theory. The code in Keras is much simpler, as we will see now. Keras allows you to build models in two different ways, using either the functional API or the sequential API. We will focus on the sequential API. This is a simple yet very powerful way of building neural networks that will get you covered for most use cases. With the sequential API, you are essentially building a model as a stack of layers. You can start with an input layer, add a couple of hidden layers, and finally end your model by adding an output layer. Let's go through a code sample. To create a simple neural network, we will do the following. First, import the sequential model from TensorFlow Keras models. Second, import a dense layer, also known as a fully connected layer, from TensorFlow Keras layers. We can then create an instance of a sequential model. In this next line of code, we add two layers, a 2-neuron dense fully connected layer and an input layer consisting of 3 neurons. The input layer is defined with the input shape parameter, and it matches the dimension of our input data. We finally add another fully connected layer, this time with 1 neuron, and we have just built the network to the right. In order to add an activation function to our layers, we can make use of the activation argument. For instance, this is how we will add a ReLU activation to our hidden layer. Don't worry about the choice of activation functions, that will be covered later on in the course. Once we have created our model, we can call the summary method on it. This displays a table with 3 columns, the first with the layer's name and type, the second with the shape of the outputs produced by each layer, and the third containing the number of parameters. These are the weights, including the bias weight of each neuron in the layer. When the input layer is defined via the input shape parameter, as we did before, it is not shown as a layer in the summary, but it is included in the layer where it was defined, in this case the dense 3 layer. That's why we see that this layer has 8 parameters. 6 parameters or weights come from the connections of the 3 input neurons to the 2 neurons in this layer. The missing 2 parameters come from the bias weights, B0 and B1, 1 per each neuron in the hidden layer. These add up to 8 different parameters, just what we had in our summary. Welcome back! We are going to learn just what you were missing to be able to save the Earth from a meteor strike. But first, let's see how to compile, train, and predict with your models. In the previous lesson, we saw how easy it was to create a model with Keras. You instantiate your sequential model, add a couple of layers and their activations, and that's it. You've built a simple model in no time. A model needs to be compiled before training. We can compile our model by calling the compile method on it. The compile method receives an optimizer, which we can see as the algorithm that will be used to update our neural network weights, and a loss function, which is the function we want to minimize during training. In this case, we chose addon as our optimizer and mean square error as our loss function. Optimizers and loss functions will be covered later on in the course, so don't worry about it for now. Compiling our model produces no output. Our model is now ready to train. Creating a model is useless if we don't train it. We train our model by calling the fit method and passing the features in xtrain, the labels in ytrain, and the number of epochs to train for. During an epoch, our entire training data passes through the network and the respective weight updates take place using backpropagation. As our model is being trained, we will get some output showing its progress. We can see the model is improving since the mean square error loss is decreasing at each epoch. To obtain predictions from our trained model, we just need to call predict on the new set of data. We can store the predictions in a variable for later use. The predictions are just numbers in a NumPy array. We will interpret this depending on our dataset and problem at hand. To quickly evaluate how well our model performs on unseen data, we can use the model's evaluate method. This performs feedforward with all samples in our test dataset, xtest. Feedforward consists in computing a model's output from a given set of inputs. It then computes the error comparing the results to the true values stored in ytest. In this particular sample, the model we trained for 5 epochs before has a mean square error of 0.25. Are you ready? A meteor is approaching the Earth, and we want to make sure it won't take us to extinction. A group of scientists is trying to estimate the orbit by using historical data gathered about previous orbits of similar meteors. Scientists have used this data, alongside their knowledge, to estimate an 8-minute orbit. That is, an orbit from minus 40 minutes to plus 40 minutes. T0 corresponds to the time of crossing the impact region. It looks like the meteor will be close. Perhaps it won't hit us, but we must make sure we are right. You have data for the path a previous meteor took during a period of 20 minutes, 10 minutes before and 10 minutes after crossing the impact region. You will train a model on this data and then extrapolate your predictions to an 80-minute orbit to see how it compares to the scientist's prediction. Will your orbit be similar to that of the scientists, or are we facing the extinction of humanity as we know it? You are now ready to learn about binary classification, so let's dive in. You will use binary classification when you want to solve problems where you predict whether an observation belongs to one of two possible classes. A simple binary classification problem could be learning the boundaries to separate blue from red circles as shown in the image. The dataset for this problem is very simple. The coordinates are pairs of values corresponding to the x and y coordinates of each circle in the graph. The labels are 1 for red circles and 0 for the blue circles. We can make use of Seaborn's pair plot function to explore a small dataset and identify whether our classification problem will be easily separable. We can get an intuition for this if we see that the classes separate well enough along several variables. In this case, for the circles dataset, there is a very clear boundary. The red circles concentrate at the center, while the blue are outside. It should be easy for our network to find a way to separate them just based on x and y coordinates. This is the neural network we will build to classify red and blue dots in our graph. We have two neurons as an input layer, one for the x-coordinate and another for the y-coordinate of each of the red and blue circles in the graph. Then, we have one hidden layer with 4 neurons. 4 is a good enough number to learn the separation of classes in this dataset. This was found by experimentation. We finally end up with a single output neuron which makes use of the sigmoid activation function. It is important to note that, regardless of the activation functions used for the previous layers, we do need the sigmoid activation function for this last output node. The sigmoid activation function squashes the neuron output of the second to last layer to a floating point number between 0 and 1. You can consider the output of the sigmoid function as the probability of a pair of coordinates being in one class or another. So we can set a threshold and say that everything below 0.5 will be a blue circle, and everything above a red one. So let's build our model in Keras. We start by importing the sequential model and the dense layer. We then instantiate a sequential model. We add a hidden layer of 4 neurons and we define an input shape, which consists of 2 neurons. We use the tan-h as the activation function for this hidden layer. Activation functions are covered later in the course, so don't worry about this choice for now. We finally add an output layer which contains a single neuron. We make use of the sigmoid activation function so that we achieve the behavior we expect from this network, that is, obtaining a value between 0 and 1. Our model is now ready to be trained. Just as before, we need to compile our model before training. We will use stochastic gradient descent as an optimizer and binary cross entropy as our loss function. Binary cross entropy is the function we use when our output neuron is using sigmoid as its activation function. We train our model for 20 epochs, passing our coordinates and labels as parameters. Then we obtain the predicted labels by calling predict on coordinates. These are the boundaries that were learned to classify our circles. It looks like our model did pretty well. What about when we have more than 2 classes to classify? We run into a multi-class classification problem. But don't worry, we just have to make a minor tweak to our neural network architecture. Identifying who threw which dart in a game of darts is a good example of a multi-class classification problem. Each dart can only be thrown by one competitor, and that means that our classes are mutually exclusive, since no dart can be thrown by 2 different competitors simultaneously. The darts dataset consists of dart throws by different competitors. The coordinate pairs x-core and y-core show where each dart landed. Based on the landing position of previously thrown darts, we should be able to distinguish between throwers if there's enough variation between their throws. In our pair plot, we can see that different players tend to aim at specific regions of the board. The model for this dataset has 2 neurons as inputs, since our predictors are x-core and y-core. We will define them using the input shape argument, just as we've done before. In between, there will be a series of hidden layers. We are using 3 dense layers of 128, 64, and 32 neurons each. As outputs, we have 4 neurons, 1 per competitor. Let's look closer at the output layer now. We have 4 outputs, each linked to a possible competitor. Each competitor has a probability of having thrown a given dart, so we must make sure that the total sum of probabilities for the output neurons equals 1. We achieve this with the Softmax activation function. Once we have a probability per output neuron, we then choose as our prediction the competitor whose associated output has the highest probability. You can build this model as we did in the previous lesson. Instantiate a sequential model, add a hidden layer, also defining an input layer with the input shape parameter, and finish by adding the remaining hidden layers and an output layer with Softmax activation. You will do all this yourself in the exercises. When compiling your model, instead of binary cross entropy, as we used before, we now use categorical cross entropy or log loss. Categorical cross-entropy measures the difference between the predicted probabilities and the true labels of the class we should have predicted. So if we should have predicted 1 for a given class, taking a look at the graph we see that we will get high loss values for predicting close to 0, since we will be very wrong, and low loss values for predicting closer to 1, the true label. Since our outputs are vectors containing the probabilities of each class, our neural network must also be trained with vectors representing this concept. To achieve that, we make use of the TensorFlow Keras utils to categorical function. We first turn our response variable into a categorical variable with pandas categorical. This allows us to redefine the column using the categorical codes, cat codes, of the different categories. Now that our categories are each represented by a unique integer, we can use the toCategorical function to turn them into one-hot encoded vectors, where each component is 0 except for the one corresponding to the labeled categories. Keras toCategorical essentially performs the process described in the picture above. Label encoded apple, chicken, and broccoli turned into a vector of 3 components. A 1 is placed to represent the presence of the class and a 0 to indicate its absence. Now that you know how multi-class classification works, we can take a look at multi-label classification. They both deal with predicting classes, but in multi-label classification, a single input can be assigned to more than one class. We could use multi-label classification, for instance, to tag a series universe by its plot summary. Making models that deal with text or images is not covered in this course in depth. We will learn more about it on Chapter 4. Imagine we had 3 classes: sun, moon, and clouds. In multi-class problems, if we took a sample of our observations, each individual in the sample will belong to a unique class. However, in a multi-label problem, each individual in the sample can have all, none, or as a set of the available classes. As you can see in the image, multi-label vectors are also one-hot encoded. There is a 1 or a 0 representing the presence or absence of each class. Making a multi-label model for this problem is not that different to what you did when building your multi-class model. We first instantiate a sequential model. For the sake of this example, we will assume that to differentiate between these 3 classes, we need to use 1 input and 2 hidden neurons. The biggest changes happen in the output layer and in its activation function. In the output layer, we use as many neurons as possible classes, but we use sigmoid activation this time. We use sigmoid outputs because we no longer care about the sum of probabilities. We want each output neuron to be able to individually take a value between 0 and 1. This can be achieved with the sigmoid activation because it constrains our neuron output in the range 0-1. That's what we did in binary classification, though we only had one output neuron there. Binary cross-entropy is now used as the loss function when compiling the model. You can look at it as if you were performing several binary classification problems. For each output, we are deciding whether or not its corresponding label is present given the current input. When training our model, we can use the validation split argument to print validation loss and accuracy as its range. By using validation split, a percentage of the training data is left out for testing at each epoch. You can see how using neural networks for multi-label classification can be performed with minor tweaks to our model architecture. If we were to use a classical machine learning approach to solve multi-label problems, we will need more complex methods. One way to do so consists of training several classifiers to distinguish each particular class from the rest. This is called one versus rest classification. Let's tackle a new problem. A farm field has an array of 20 sensors distributed along 3 crop fields. These sensors measure, among other things, the humidity of the soil, radiation of the sun, etc. Your task is to use the combination of measurements from these sensors to decide which parcels to water, given each parcel has a different environmental requirement. Each sensor measures an integer value between 0 and 13 volts. Parcels can be represented as one-hot encoded vectors of length 3, where each index is one of the parcels. Parcels can be watered simultaneously. By now you've trained a lot of models. It is time to learn more about how to better control and supervise model training by using callbacks. A callback is a function that is executed after some other function, event, or task has finished. For instance, when you touch your phone screen, a block of code that identifies the type of gesture will be triggered. Since this block of code has been called after the touching event occurred, it is a callback. In the same way, a Keras callback is a block of code that gets executed after each epoch during training or after the training is finished. They are useful to store metrics as the model trains and to make decisions as the training goes by. Every time you call the fit method on a Keras model, there is a callback object that gets returned after the model finishes training. This is the history object. Accessing the history attribute, which is a Python dictionary, we can check the saved metrics of the model during training as an array of numbers. To get the most out of the history object, we should use the validation data parameter in our fit method, passing xtest and ytest as a tuple. The validation split parameter can be used too, specifying a percentage of the training data that will be left out for testing purposes. That way, we not only have the training metrics, but also the validation metrics. You can compare training and validation metrics with a few matplotlib commands. We just need to define a figure, plot the values of the history attribute for the training accuracy and the validation accuracy. We can then make our graph prettier by adding a title, axis labels, and a legend. We can see our model accuracy increases for both training and test sets till it reaches epoch 25. Then, accuracy flattens for the test set, which the training keeps improving. Overfitting is taking place, since we see the training accuracy keeps improving whilst the text data decreases in accuracy. More on this in the next chapter. Early stopping a model can solve the overfitting problem, since it stops training when it no longer improves. This is extremely useful since deep neural models can take a long time to train, and we don't know beforehand how many epochs will be needed. Early stopping, like the other Keras callbacks, can be imported from TensorFlow Keras callbacks. We don't need to instantiate it. The early stopping callback can monitor several metrics, like validation accuracy, validation loss, etc. This can be specified in the monitor parameter. It is also important to define a patient argument, that is the number of epochs to wait for the model to improve before stopping its training. There's no rules to decide which patient number works best at all times. This depends on the implementation. It is good to avoid low values, that way your model has a chance to improve at a later epoch. The callbacks is passed as a list to the callbacks parameter in the model fit method. The model checkpoint callback can also be imported from Keras callbacks. This callback allows us to save our model as it trains. We specify the model file name with a name and the .htf5 extension. You can also decide what to monitor to determine which model is best with the monitor parameter. By default, validation loss is monitored. Setting the save best only parameter to true guarantees that the latest best model according to the quantity monitor will not be overridden. Learning curves provide a lot of information about your model. Now that you know how to use the history callback to plot them, you will learn how to read them to get the most value out of them. So far, we've seen two types of learning curves: loss curves and accuracy curves. Loss tends to decrease as epochs go by. This is expected, since our model is essentially learning to minimize the loss function. Epochs are shown on the x-axis, and loss on the y-axis. As epochs go by, our loss value decreases. After a certain amount of epochs, the value converges, meaning it no longer gets much lower than that. We have arrived at a minimum. Accuracy curves are similar but opposite in tendency. If the y-axis shows accuracy, it now tends to increase as epochs go by. This shows that our model makes fewer mistakes as it learns. If we plot training versus validation data, we can identify overfitting. We will see that the training and validation curves start to diverge. Overfitting is when our model starts learning particularities of our training data which don't generalize well on unseen data. The early stopping callback is useful to stop our model before it starts overfitting. But not all curves are smooth and pretty. Many times we will find unstable curves. There are many reasons that can lead to unstable learning curves: the chosen optimizer, learning rate, batch size, network architecture, weight initialization, etc. All of these parameters can be tuned to improve our model learning curves, as we aim for better accuracy and generalization power. We will cover this in the following videos. Neural networks are well known for surpassing traditional machine learning techniques as we increase the size of our datasets. We can check whether collecting more data will increase a model's generalization and accuracy. We aim at producing a graph like this one, where we have fitted our model with increasing amounts of training data and plotted the values for the training and text accuracies of each run. If after using all our data, we see that our test still has a tendency to improve, that is, it is not parallel to our training set curve and it is increasing, then it is worth it to gather more data if possible to allow the model to keep learning. How will we go about coding a graph like the previous one? Imagine we want to evaluate an already built and compiled model and that we have partitioned our data into X-train, Y-train, X-test and Y-test. We first store the model initial weights. This is done by calling getWeights on our model. We then initialize two lists to store train and test accuracies. We loop over a predefined list of train sizes, and for each training size, we get the corresponding training data fraction. Before any training, we make sure our model starts with the same set of weights by setting them to the initial weights using the setWeights function. After that, we can fit our model on the training fraction. We use an early stopping callback which monitors loss, but it is important to note that it's not validation loss since we haven't provided the fit method with validation data. After the training is done, we can get the accuracy for the training set fraction and the accuracy from the test set and append it to our list of accuracies. Observe that the same quantity of test data observations were used to evaluate each iteration. So far, we have been using several activation functions in our models, but we haven't yet covered their role in neural networks other than when it comes to obtaining the output we want in our output layer. Inside the neurons of any neural network, the same process takes place. A summation of the inputs reaching the neuron multiplied by the weights of each connection and the addition of the bias weight. This operation results in a number, A, which can be anything. It is not bounded. We pass this number into an activation function that essentially takes it as an input and decides how the neuron fires and which output it produces. Activation functions impact learning time, making our model converge faster or slower and achieving lower or higher accuracy. They also allow us to learn more complex functions. Four very well-known activation functions are the sigmoid, which varies between 0 and 1 for all possible x input values. The tanh, or hyperbolic tangent, which is similar to the sigmoid in shape, but varies between -1 and 1. The ReLU, rectified linear unit, which varies between 0 and infinity. And the leaky ReLU, which we can look as a smoothed version of ReLU that doesn't sit at 0, allowing negative values for negative inputs. Changing the activation function used in the hidden layer of the model we built for binary classification results in different classification boundaries. We can see that the previous model cannot completely separate red crosses from blue circles if we use a sigmoid activation function in the hidden layer. Some blue circles are misclassified as red crosses along the diagonal. However, when we use the tanh, we completely separate red crosses from blue circles. The separation region for the blue and red classification is smooth. Using a ReLU activation function, we obtain sharper boundaries. The leaky ReLU shows similar behavior for this dataset. It is important to note that these boundaries will be different for every round of the same model because of the random initialization of weights and other random variables that aren't fixed. All activation functions come with their pros and cons. There's no easy way to determine which activation function is best to use. Based on their properties, the problem at hand, and the layer we are looking at in our network, one activation function will perform better in terms of achieving our goal. A way to go is to start with ReLU, as they train fast and will tend to generalize well to most problems, avoid sigmoids, and tune with experimentation. It is easy to compare how models with different activation functions perform if they are small enough and train fast. It is important to set a random seed with NumPy. That way, the model weights are initialized the same for each activation function. We then define a function that returns a fresh new model each time, using the act function parameter. We can then use this function as we loop over several activation functions, training different models and saving their history callback. We store all of these callbacks in a dictionary. With this dictionary of histories, we can extract the metrics we want to plot, build a pandas data frame, and plot it. It is time to learn the concepts of batch size and batch normalization. A mini-batch is as a set of data samples. If we were training a neural network with images, each image in our training set will be a sample, and we could take many batches of different sizes from the training set batch. Remember that during an epoch we fit our network, calculate the errors, and update the network weights. It is not very practical to update our network weights only once per epoch, after looking at the error produced by all training samples. In practice, we take a mini batch of training samples, and that way, if our training set has 9 images and we choose a batch size of 3, we will perform 3 weight updates per epoch, 1 per mini batch. Networks tend to train faster with mini batches, since weights are updated often. Sometimes datasets are so huge that they will struggle to fit in RAM memory if we didn't use mini batches. Also, the noise produced by a small batch size can help escape local minima. A couple of disadvantages are the need for more iterations and finding a good batch size. Here, you can see how different batch sizes converge towards a minimum as training goes by. Training with all samples is shown in blue, mini batching is shown in green, stochastic gradient descent in red uses a batch size of 1. We can see how the path towards the best value for our weights is noisier the smaller the batch size. They reach the same value after a different number of iterations. You can set your own batch size with the batch size parameter on the model's fit method. Keras uses a default batch size of 32. Increasing powers of 2 tend to be used. As a rule of thumb, you tend to make your batch size bigger the bigger your dataset. Normalization is a common preprocessing step in machine learning algorithms, especially when features have different scales. One way to normalize data is to subtract its mean value and divide by the standard deviation. We always tend to normalize our model inputs. This avoids problems with activation functions and gradients. This leaves everything centered around 0 with a standard deviation of 1. Normalizing neural networks inputs improves our model, but deeper layers are trained based on previous layer outputs, and since weights get updated via gradient descent, consecutive layers no longer benefit from normalization, and they need to adapt to previous layers' weight changes, finding more trouble to learn their own weights. Batch normalization makes sure that, independently of the changes, the inputs to the next layer are normalized. It does this in a smart way, with trainable parameters that also learn how much of this normalization is kept scaling or shifting it. This improves gradient flow, allows for higher learning rates, reduces weight initialization dependence, adds regularization to our networks, and limits internal covariate shift, which is a funny name for a layer's dependence on the previous layer outputs when learning its weights. Batch normalization is widely used today in many deep learning models. Batch normalization in Keras is applied as a layer, so we can place it in between 2 layers. We import batch normalization from TensorFlow Keras layers. We then instantiate a sequential model, add an input layer, and then add a batch normalization layer. We finalize this binary classification model with an output layer. You now know everything you need to perform hyperparameter tuning in neural networks. Our aim is to identify those parameters that make our model generalize better. A neural network is full of parameters that can be tweaked. The number of layers, neurons per layer, the order of such layers, the activation functions, batch sizes, learning rate optimizers, a lot of things to keep in mind. In scikit-learn, we can perform hyperparameter search by using methods like RandomizedSearchCV. We import RandomizedSearchCV from scikit-learn model selection. We instantiate a model, define a dictionary with a series of model parameters to try, and finally instantiate a RandomizedSearchCV object passing our model, the parameters, and a number of cross-validation faults. We feed it on our data and print the best resulting combination of parameters. For this example, a mean sample lift of 1, 3 max features, and a max depth of 3 gave us the best results. We can do the same with our Keras models, but we first have to transform them into scikit-learn estimators. We do this by first defining a function that creates our model. Then, we import the Keras classifier wrapper from TensorFlow Keras scikit-learn wrappers. We finish by simply instantiating a Keras classifier object, passing createModel as the built-in function. Other parameters like epochs and batch size are optional, but should be passed if we want to specify them. This is very cool. Our model is now just like any other scikit-learn estimator, so we can, for instance, perform cross-validation on it to see the stability of its predictions across faults. Import crossval score, passing in our recently converted Keras model, predictors, labels, and the number of faults. We can then check the mean accuracy per fold or the standard deviation. Note that 6 epochs and a batch size of 16 were used since we specified it before. It is much more probable that a good combination of parameters will be found by using random search instead of an exhaustive grid search. Grid search loops over all possible combinations of parameters, whilst random search tries a given number of random combinations. Normally, not many epochs are needed to check how well your model is performing. Using a smaller representative sample of your dataset makes it faster if you've got a huge dataset. It is easier to play with things like optimizer, batch sizes, activations, and learning rates. To perform randomized search on a Keras model, we just need to define the parameters to try. We can try different optimizers, activation functions for the hidden layers, and batch sizes. The keys in the parameter dictionary must be named exactly as the parameters in our createModel function. We then instantiate a RandomizedSearchCV object passing our model and parameters with threefold cross-validation. We end up fitting our random search object to obtain the results. We can print the best score and the parameters that were used. We get an accuracy of 94% with the add-on optimizer, 3 epochs, a batch size of 10, and redo activation. Parameters like the number of neurons per layer and the number of layers can also be tuned using the same method. We just need to make some smart changes in our createModel function. The NL parameter determines the number of hidden layers and NN the number of neurons in these layers. We can have a loop inside our function and add to our sequential model as many layers as provided in NL with the given number of neurons. Then, we just need to use the exact same names in the parameter dictionary as we have in our function and repeat the process. The best result is 87% accuracy with 2 hidden layers of 128 neurons each. Now that you know how to tune your models, it is time to better understand how they work internally and to explore newer network architectures. Model layers are easily accessible. We just need to call layers on a built model and access the index of the layer we want. From a chosen layer, we can print its inputs, outputs, and weights. You can see inputs and outputs are tensors of a given shape built with TensorFlow tensor objects. Weights are TensorFlow variable objects, which are just tensors that change their value as the neural network learns the best weights. Tensors are the main data structures used in deep learning. Inputs, outputs, and transformations in neural networks are all represented using tensors and tensor multiplication. A tensor is a multidimensional array of numbers. A two-dimensional tensor is a matrix. A three-dimensional tensor is an array of matrices. If we import the Keras backend, we can build a function that takes in an input tensor from a given layer and returns an output tensor from another of the same layer. TensorFlow is the backend Keras is using in this course, but it could be any other, like Fiano. To define the functions with our backend K, we need to give it a list of inputs and outputs, even if we just want one input and one output. Then, we can use it on a tensor with the same shape as the input layer given during its definition. If the weights of the layer between our input and output change, the function output for the same input will change as well. We can use this to see how the output of certain layers change as weights are adjusted during training. We will check this in the exercises. It is time to introduce a new architecture, Autoencoders. Autoencoders are models that aim at producing the same inputs as outputs. This task alone wouldn't be very useful, but since along the way we decrease the number of neurons, we are effectively making our network learn to compress its inputs into a smaller set of neurons. This makes autoencoders useful for things like dimensionality reduction, since we can obtain a smaller dimensional space representation of our inputs. Denoising, if trained with clear data and then fed with noisy data, they will be able to decode back a good representation of the input data without noise. Anomaly detection, if you train an autoencoder to map inputs to output with data but you then pass in strange values, the network will fail at giving accurate output values, and we can measure this as a loss. Many other applications can also benefit from this architecture. To make an autoencoder that maps 100 inputs to 100 outputs, encoding the inputs into a layer of 4 neurons, we will do the following. Instantiate a sequential model. Add a dense layer of 4 neurons with an input shape of 100 and n with an output layer of 100 neurons. We use activation sigmoid because we assume that our output can take a value between 0 and 1. We end compiling our model with an optimizer and binary cosentropy loss since we use sigmoid. Once you've built and trained your autoencoder, you might want to encode your inputs. To do this, you just have to build a new model which uses the first layer of your previously trained autoencoder. This new model predictions returns the 4 numbers given by the 4 neurons of the hidden layer. It is effectively returning a 4 number encoding of each observation in the input dataset. Let's introduce convolutional neural networks, a different type of network that has led to a lot of advances in computer vision, as well as in many other areas. A convolutional model uses convolutional layers. A convolution is a simple mathematical operation that preserves spatial relationships. When applied to images, it can detect relevant areas of interest like edges, corners, vertical lines, etc. It consists of applying a filter, also known as a kernel, of a given size. In this image, we are applying a 3x3 kernel. We center the kernel matrix of numbers as we slide through each pixel in the image, multiplying the kernel and pixel values at each location and averaging the sum of values obtained. This effectively computes a new image where certain characteristics are amplified depending on the filter used. The secret sauce of CNNs resides in letting the network itself find the best filter values and to combine them to achieve a given task. For a classification problem with many possible classes, CNNs tend to become very deep. Architectures consist of concatenations of convolutional layers among other layers known as pooling layers, that we won't cover here. Convolutional layers perform feature learning. We then flatten the outputs into a unidimensional vector and pass it to fully connected layers that carry out classification. Images are 3D tensors. They have width, height, and depth. This depth is given by the color channels. If we use black and white images, we will just have one channel, so the depth will be 1. To build a CNN in Keras, we first import the convolutional 2D and flatten layers from TensorFlow Keras layers. We instantiate our model and add a convolutional layer. This first convolutional layer has 32 filters. This means it will learn 32 different convolutional masks. This mask will be squares of 3x3 as defined in the kernel size. For 28 x 28 black and white images with only one channel, we use an input shape of 28, 28, 1. We can use any activation, as usual. We then add another convolutional layer and then flattening this 2D layer into a unidimensional layer with a flattened layer. We finish with an output dense layer. ResNet 50 is a 50-layer deep model that performs well on the ImageNet dataset, a huge dataset of more than 40 million images. ResNet 50 can distinguish between 1,000 different classes. This model would take too long to train on a regular computer, but Keras makes it easy for us to use it. We just need to prepare the image we want to classify for the model, predict the processed image, and decode the predictions. To use pre-trained models to classify images, we first have to adapt these images so that they can be understood by the model. To prepare images for ResNet 50, we will do the following. First, import image from TensorFlow Keras preprocessing, and preprocess input from TensorFlow Keras application ResNet 50. We then load our image with load image, providing the target size. For this particular model, that is 224 by 224. We turn the image into a NumPy array with image to array. We expand the dimensions of the array and preprocess the input in the same way the training images were. We import ResNet 50 and decode predictions. Load the model with ImageNet pre-trained weights, predict on our image, and decode the predictions. That is, getting the predicted classes with the highest probabilities. Inside a CNN, we can check how the different filters activate in response to an input image. We will explore this in the exercises. It is time to briefly introduce long short-term memory networks, also known as LSTMs. LSTMs are a type of recurrent neural network, RNN for short. A simple RNN is a neural network that can use past predictions in order to infer new ones. This allows us to solve problems where there is a dependence on past inputs. LSTM neurons are pretty complex. They are actually called units or cells. They have an internal state that is passed between units. You can see this as a memory of past steps. A unit receives the internal state, an output from the previous unit, and a new input at time t. Then, it updates the state and produces a new output that is returned, as well as passed as an input to the following unit. LSTM units perform several operations. They learn what to ignore, what to keep, and to select the most important pieces of past information in order to predict the future. They tend to work better than simple RNNs for most problems. LSTMs have been used for image captioning, speech-to-text, text translation, document summarization, text generation, musical composition, and many more. Let's go over an example on how to use LSTMs with text data to predict the next word in a sentence. Neural networks can only deal with numbers, not text. We need to transform each unique word into a number. Then, these numbers can be used as inputs to an embedding layer. Embedding layers learn to represent words as vectors of a predetermined size. These vectors encode meaning and are used by subsequent layers. We first define some text and choose a sequence length. With a sequence length of 3, we will end up fitting our model with 2 words, and it will predict the third one. We split the text into words with the split method. The output looks like this. We then need to turn these words into consecutive lines of 3 words each. We can loop from sequence length to the number of words plus 1 and store each line. The end results looks like this. After that, we turn our text sequences into numbers. We import Keras tokenizer from the preprocessing text module, instantiate it, fit it on lines, and then turn those lines into numeric sequences. This is how the 3-word lines look now. The tokenizer object stores the word-to-number mapping. There are 2 dictionaries, the index word and the word index. Here, the index word is printed, which shows the encoded word for each index. We can use this dictionary to decode our outputs, mapping numbers back to words. Our data is ready to be processed. Now, we are ready to build the LSTM model. We start by importing the dense, LSTM, and embedding layers from TensorFlow Keras layers. We then store the vocab size, since we will use it when defining our layers. The vocab size is the length of the tokenizer dictionary plus 1. The plus 1 is because we account for 0 as an integer reserved for special characters. As we saw, our dictionary starts at 1, not 0. We add an embedding layer. The input dimension is the vocab size variable. We will turn our word numbers into 8-dimensional vectors, and need to declare the input length so that our model understands that 2 words will be passed simultaneously as a sequence. We end by adding an LSTM layer of 8 units, a hidden layer, and an output layer with Softmax and as many outputs as possible words. If you have finished the whole course, you have probably put a lot of energy and work into understanding all of these new concepts. So, congratulations! I hope you have fun. Now you have a better understanding of many key points when it comes to building a variety of neural networks and what you can use them for. You have learned a lot. You completed 44 exercises and 14 lessons. You should be proud. You have a lot of power in your hands. You have learned the basics of neural networks, built sequential models, and learned to solve regression, binary classification, multiclass, and multilabel problems with neural networks. You have explored activation functions and carried out hyperparameter tuning, turning your Keras models into scikit-learn estimators. You have used autoencoders and denoised images with them. You have learned key concepts about CNN networks and used the pre-trained ResNet50 model to classify images. You visualized convolutions for the MNIST dataset. You learned about LSTM concepts and worked with text and embedding layers. You've used a lot of different datasets along the way, also learning a lot of Keras utility functions. To keep on improving your understanding and learning on neural networks, you should go deeper into CNNs. There is a specific course here on DataCamp. You can also go deeper into LSTMs. There's a lot more to learn. You could also check how to work with the Keras Functional API, which allows you to build more powerful models with shared layers and several branches. And finally, consider getting creative with generative adversarial networks and taking on some deep learning projects of your own. If you like this course, consider spreading the word so other people can also experience your journey. And feel free to give me a follow on Twitter or LinkedIn if you would like. And remember, your adventures with neural networks just begun.
Hi, I'm Zach Dean Mayer, and in this course, I'll be teaching you advanced deep learning concepts using the Keras Functional API. You will learn how to build functional Keras models, including advanced topics such as shared layers, categorical embeddings, multiple inputs, and multiple outputs. The Keras Functional API is extremely simple, yet immensely powerful. By the end of this class, you will build a model that is capable of solving a regression and a classification problem at the same time. Chapter 1 is a refresher on building simple models, where you will learn how to use the Keras functional API. In Chapter 2, you will build a Keras model with 2 inputs. In Chapter 3, you will learn how to generalize your 2-input model to 3 or more inputs. And finally, in Chapter 4, you will build models with multiple outputs that can solve multiple problems. You will be using 2 datasets of college basketball games from American colleges. The first dataset is from the regular season and has the following data: the IDs of the 2 teams that played, whether the first team was home or away, whether the first team won or lost the game, and by how many points the first team won or lost. For the tournament dataset, you also have the tournament seed, which is a pre-tournament ranking for each team. These seeds range from 1 to 16, where the best 4 teams get a seed of 1, and the worst 4 teams get a seed of 16. You will use the difference in the 2 teams' seeds as an input to your model. Here are the first 5 rows of both the datasets. You can see that the team variables are encoded as integers, and the tournament dataset has 1 additional column, the difference between the tournament seeds for both teams. Other than the seed difference, the 2 datasets have identical columns. Within a given year, a team's roster stays relatively constant, but between years it can change a lot as seniors graduate and freshmen start. Therefore, for every year, each school is given a unique integer ID. Keras models, at their simplest, are fundamentally composed of 2 parts, an input layer and an output layer. To start, I'll define a very simple Keras model which only expects a single input. I'll specify this using the input function from the keras.layers module. The number of columns in the input is specified using the shape parameter. This tells the model how much data to expect. Note that the shape argument expects a tuple. The input function returns a tensor. If you print this tensor, you'll see that it is a tf.tensor object, which indicates it is ready to be used by our model as input. Now that we've defined our input layer, let's define the output layer. Outputs in Keras are most commonly a single dense layer, which specifies the shape of the expected output. In this case, we are expecting our model to predict a single value, so we pass 1 unit to the dense layer. If you print the output layer, the result is not a TensorFlow tensor. It is a function, which takes a tensor as input and produces a tensor as output. The difference between layers and tensors is key to understanding the Keras functional API. Layers are used to construct a deep learning model, and tensors are used to define the data flow through the model. In this case, the input layer defines a tensor, which we then pass to the output layer function. The final output of our model is a tensor. In this lesson, I will show you how to turn the collection of layers you assembled in Lesson 1 into an actual model that you can fit to the data and then use to predict on new data. I will start with the 2 simple Keras layers you defined in Lesson 1. Note that I've taken a shortcut here. Rather than defining the output layer in one line and then the output tensor in the next, I'm using one line to both create the layer function and then call it to produce a tensor. There are 2 sets of parentheses in that line because we both create the function and then call it in the same line. To build a model, you simply import the model class from keras.models and pass your input and output to this class. In this case, we only have a single input and a single output, which we pass directly to the model. However, later in this class, you will work with multiple inputs and multiple outputs in which case you will pass lists of inputs or lists of outputs to the model. Finally, you must compile the model before fitting it to data. The compilation step finalizes the model and gets it completely ready for use in fitting and predicting. During compilation, you select an optimizer. I almost always use the Atom optimizer, and you will find it typically gives good results. During compilation, you also select a loss function. In this case, we use mean absolute error, which is a good general-purpose error function for Keras models, as it is a little bit less sensitive to outliers. You could also use mean squared error, which would be equivalent to traditional linear regression. Before fitting my models, I also like to summarize them. You can do this by calling the summary method on the model object. This gives you a nice table of the layers in the model, so you can confirm they are as you expect. In this case, you can see your input layer and your output layer. The output layer has two parameters, which makes sense as you have one input and one output. The model you have defined here is a standard linear regression model, equivalent to y equals mx plus b. M and b are the two parameters. In the terminology of linear regression, m is the slope and b is the intercept. In the terminology of Keras, m is the weight of the dense layer and b is the bias of the dense layer. It is also useful to plot the model before fitting it. A plot gives you a little bit more information than a summary. It shows you how the layers connect together visually. In this case, the input layer connects directly to the output layer, which is dense. Note that in the code for this example, I've named the dense layer. Names are useful when you're looking at model plots to help keep track of which layer in the plot is which layer in the code. Plot model saves the image to a file, which we can then display using matplotlib's imread and imshow functions, as shown here. In this lesson, you will take the model you compiled in Lesson 2 and fit it to college basketball data. Your goal is to predict which team will win a tournament game. The only data you have to work with are the team's seeds, which are assigned by the tournament organizers and are a rating of how good the team is. A seed of 1 is a very good team, and a seed of 16 is a very bad team. In the 30-plus year history of the tournament, a 16 seed has beat a 1 seed exactly once. It was in 2018, which was a very exciting year for college basketball fans. Your input will be the difference in seed between the two teams. For example, if a 7 seed plays a 10 seed, their seed difference is 7 minus 10, or -3. If an 11 seed plays a 7 seed, their seed difference is 11 minus 7, or 4. Your output will be the difference in score between the two teams. For example, if Team 1 scores 41 points and Team 2 scores 50 points, the score difference is 41 minus 50, or -9. On the other hand, if Team 1 scores 61 points and Team 2 scores 55 points, the score difference is 61 minus 55, or +6. Therefore, your model has one input and one output. This is exactly the model you created in Lesson 1 and Lesson 2 of this chapter. You will use the difference in seeds as your input. Note that you have both a 16 seed playing a 1 seed and a 1 seed playing a 16 seed in your data, so you'll have seed differences ranging from -15 to +15. A seed difference of +15 means that Team 1 has a seed of 16 and is playing a team of seed of 1. This means Team 1 is likely, though not certain, to lose. A seed difference of -15 means that Team 1 has a seed of 1 and is playing a team of seed of 16. This means Team 1 is likely, though not certain, to win. So a positive seed difference is usually predictive of a negative score difference, and a negative seed difference is usually predictive of a positive score difference. Our target variable is the game score difference and ranges from about -50 to +50. This means you have games where Team 1 lost by 50 points and games where they won by 50 points. Note that both the regular season and the tournament datasets have 2 rows per game, where the second row has the opposite signs of the first row. In other words, for a given game where the first team won, there is also a row in the dataset where Team 1 and Team 2 are swapped and the first team lost. Here is the model from lessons 1 and 2 defined in a single code chunk. This is a very basic Keras regression model with 1 input and 1 output. You could use this model for any regression problem with a single predictor and a single outcome. To fit the model, load the basketball tournament dataset from a CSV file using pandas, and then call model.fit. Use the seed diff column from the dataset as the input, and the score diff column from the dataset as the output. The fit method has some additional arguments which can be useful. Batch size sets how many rows of data are used for each step of stochastic gradient descent. In this case, you'll train on 64 rows at a time. Validation split tells Keras to use a holdout set and return metrics on accuracy using that data. This can be useful for validating that your models will perform well on new data. When verbose is set to true, Keras prints a log during training. This can be useful for debugging, but usually I set it to false once I like how the model works. Once you fit a model, it is useful to evaluate it on new data. Even if you use a validation set during training, you often want to do a second check using a new data set to make sure the model is predicting as expected. To do this, you can use the evaluate method of the model and pass it the x and y variables from the new data. When you do this, Keras will report error metrics on the new data. In Chapter 1, our dataset of tournament games only contained about 4,000 rows. However, we have a much bigger dataset with over 300,000 regular season games. Let's see what we can learn from a much larger sample of data. In the 2 basketball datasets you will be using in this course, there are a little under 11,000 teams. Each team is coded as an integer starting with 1 and ending with 10,887. In this lesson, you will learn how to use those team IDs as inputs to a model that learns the strength of each team. Categorical embeddings are an advanced type of layer only available in deep learning libraries. They are extremely useful for dealing with high cardinality categorical data. In this dataset, the team ID variable has high cardinality. Embedding layers are also very useful for dealing with text data, such as in word-to-vec models, but that is beyond the scope of this course. To model these teams in the basketball data, you'll use a very simple model that learns a strength rating for each team and uses those ratings to make predictions. To map the integer team IDs to a decimal rating, we will use an embedding layer. To get started with category embeddings, you will need an input layer. In this case, your input is a single number ranging from 1 to 10,887, which represents each team's unique ID. Note that this dataset covers about 30 years of data and has about 400 unique schools, giving us close to 12,000 IDs. We only have about 11,000 of those team year combinations because not every school has a basketball team every year. To create an embedding layer, use the embedding function from keras.layers. Since you have 10,887 unique teams in the dataset, you will define the input dimension of the embedding layer as 10,887. As you are representing each team as a single integer, use an input length of 1. You want to produce a single team strength rating, so use an output dimension of 1. Finally, name your layer so you can easily find it when looking at the model summary or plot. To use the embedding layer, connect it to the tensor produced by the input layer. This will produce an embedding output tensor. Embedding layers increase the dimensionality of your data. The input CSV has 2 dimensions, rows and columns, but the embedding layers add a 3rd dimension. This 3rd dimension can be useful when dealing with images and text, so it is not as relevant to this course. Therefore, we use the flatten layer to flatten the embeddings from 3D to 2D. The flatten layer is also the output layer for the embedding process. Flatten layers are an advanced layer for deep learning models and can be used to transform data from multiple dimensions back down to 2 dimensions. They are useful for dealing with time series data, text data, and images. Now you can wrap your embedding layer in a model. This will allow you to reuse the model for multiple inputs in the dataset. You do this by defining an input layer, and then an embedding layer, then a flatten layer for the output. Finally, wrap the input tensor and flatten tensor in a model. This model can be treated exactly the same as a layer and reused inside of another model. In this chapter, you will create a model with 2 inputs, one for each team in the basketball dataset. However, you want these 2 teams to each use the same embedding layer you defined in the previous lesson. Accomplishing this requires a shared layer. Shared layers are an advanced deep learning concept and are only possible with the Keras functional API. They allow you to define an operation and then apply the exact same operation with the exact same weights on different inputs. In this model, we will share team rating for both inputs. The learned rating will be the same whether it applies to team 1 or team 2. To create a shared layer, you must first create 2 or more inputs, each of which will be passed to the shared layer. In this case, you will use 2 inputs. Once you have 2 inputs, the magic of the Keras functional API becomes apparent. Recall from chapter 1 that the dense function returns a function as its output. This function, which dense outputs, takes a tensor as input and produces a tensor as output. You can use the same dense function to create a shared layer. Doing so is as simple as calling the function twice with a different input tensor each time. Recall the category embedding model we made in the previous lesson. This model first embeds an input and then flattens it. You can also share models, not just layers. This is really cool and is what makes the functional API so useful. You can define modular components of models and then reuse them. We define an embedding layer and wrap it in a model. We then define 2 input tensors and pass each one to the same model, producing 2 output tensors. This will use the same model with the same layers and the same weights for mapping each input to its corresponding output. In other words, you can take an arbitrary sequence of Keras layers and wrap them up in a model. Once you have a model, you can reuse that model to share that sequence of steps for different input layers. Now that you've got multiple inputs and a shared layer, you need to combine your inputs into a single layer that you can use to predict a single output. This requires a merge layer. Merge layers allow you to define advanced, non-sequential network topologies. This can give you a lot of flexibility to creatively design networks to solve specific problems. There are many kinds of merge layers available in Keras. Add, subtract, and multiply layers do simple arithmetic operations by element on the input layers and require them to be the same shape. For example, if we wanted to multiply our team strength ratings together, we could use a multiply layer. Concatenate layers simply append the two layers together, similar to the hstack function from NumPy. Unlike the other merge layers, the concatenate layer can operate on layers with different numbers of columns. Let's build a simple Keras model that takes in two numbers and adds them together. You can accomplish this by defining two input layers and using the add layer to add them together. If you'd like to add together many inputs, you can pass a list with more than two elements to an add layer. Note that all of the inputs are required to have the same shape, so they can be combined element-wise. The subtract and multiply layers work the same way. Now you can wrap the output from your add layer inside a model, which will then allow you to fit it to data. Note that the model takes in a list of inputs because it has more than one input. As with other Keras models, you need to compile it before fitting. Use the atom optimizer and mean absolute error as loss function. Keras models with multiple inputs work just like Keras models with a single input. They use the same fit, evaluate, and predict methods. The only difference is that all of these methods take a list of inputs rather than a single input. To fit a model with multiple inputs, provide the model a list of inputs. In this case, since you have two inputs, the model needs to have an input list of length 2. You want to use this model to predict a single target, so the target for training is still a single object. While this network is very simple, the concept it illustrates is quite advanced. Later in the course, you will process different inputs to the network in different ways. In other words, multiple inputs let you do data preprocessing as part of the model you learn. To make predictions from a model with two inputs, you also need to provide two inputs to the model's predict method, again as a list. In this case, I've defined a model that adds numbers. So in order to add 1 and 2, first convert 1 and 2 into 2D NumPy arrays. Then pass 1 as the first input and 2 as the second input. The model outputs 3. Note that the data type of the output is float32. You can also add other numbers with this simple model, for example, 42 and 119, which add up to 161. To evaluate a model with multiple inputs, simply give it a list of inputs along with a single output, and the model will return its loss on the new data. In this case, since I've hard-coded the model to add the two inputs, the evaluation error on the test data is 0. In this chapter, you'll extend your two-input model to 3 inputs and beyond. This demonstrates the power of the Keras functional API. Once you have learned how to work with two-input networks, it is trivial to extend that knowledge to 3 or more input networks. Making a Keras model with 3 inputs is almost exactly the same as making a Keras model with 2 inputs. To start, create 3 different input layers. In this case, you'll use a concatenate layer to combine the inputs. But recall from the previous chapters that you could also use an add or subtract layer. In the concatenate layer, simply pass a list of 3 inputs rather than 2. Finally, add a dense layer to reduce the 3 inputs to a single output. When creating a model with 3 inputs, simply pass a list with 3 input layers and 1 output layer. In the exercises for this chapter, you will also practice using a shared layer in a model with more than 2 inputs. For example, you can pass the first 2 inputs to a shared layer, and then concatenate the result of that shared layer with the 3rd input. In other words, you can define a Keras model in any way you want. This gives you a lot of flexibility to customize the model to the problem you want to solve. As before, we pass the original 3 inputs to the model function when creating a model. As with any Keras model, you must compile it before fitting. During compilation, you specify a loss function and an optimizer. When fitting a 3-input model, provide a list with 3 input columns, rather than 2. Since this model only has 1 output, use a single output in your model. Similarly, when evaluating your model on new data, using model.evaluate, pass 3 inputs in a list and 1 output. In this lesson, you will take a closer look at your 3-input model using Keras's built-in summary and plot methods. Here is the summary for a Keras model. The summary shows you all the layers in the model, as well as how many parameters each layer has. Importantly, Keras models can have non-trainable parameters that are fixed and do not change, as well as trainable parameters that are learned from the data when the model is fit. Models with more trainable parameters are typically more flexible. This can also make them more prone to overfitting. Models with fewer trainable parameters are less flexible, but therefore less likely to overfit. In this case, the model has 3 inputs. Since all 3 of them feed into one dense layer, the model has 4 parameters, 1 per input plus a bias or intercept. All of these parameters are trainable. A model's trainable parameters are usually in its dense layers. Here is the summary of a slightly more complicated model. You can see that this model has an embedding layer. Even though the dense layer still only has 4 parameters, the model has many more trainable parameters because of the embedding layer. It's important to remember that embedding layers often add a very large number of trainable parameters to a model. Recall that embedding layers map integers to floats. Each unique value of the embedding input gets a parameter for its output. Here is the plot for a very complicated model. The box at the bottom of the image represents the model's output. In this case, the model has 1 output. Note that output layers have arrows coming in, but no arrows going out. The boxes in the middle of the image represent intermediate steps in the model. These boxes have arrows coming in and arrows going out. Note that this model has a shared model, the team strength model, which is applied to 2 of the inputs before they are combined in the concatenate layer with the 3rd input. The boxes at the top of the image represent the inputs. These boxes only have 1 arrow going out and none coming in. Here's another way of looking at the same model using the network diagrams I've made for the previous chapter's models. Shared models work exactly the same as shared layers. This is a useful abstraction because you can put together a sequence of layers to define a custom model, and then share the entire model in exactly the same way you'd share a layer. It's a little prettier when you make them by hand, but the auto-plotting function in Keras does a good job representing the actual structure of the model. In this video, I will introduce you to the concept of model stacking, or using the predictions from one model as an input to another model. Model stacking is a very advanced data science concept. It is the most sophisticated way of combining models and, when done right, can yield some of the most accurate models in existence. Model stacking is often employed to win popular predictive modeling competitions. In this course, you have been working with two data sets: the college basketball data from the regular season and the college basketball data from the postseason tournament. Both data sets contain the two teams playing, whether team one is home or away, and the score difference of the games. The tournament data set additionally contains the difference in seeds of the two teams playing. There's a lot more data on regular season games than there is on tournament games. The regular season dataset has over 300,000 rows, but the tournament dataset has only about 4,000 rows. 4,000 rows of data is pretty small. Recall that our embedding layer has about 11,000 inputs. 4,000 rows of data is not enough to learn all 11,000 parameters in our embedding layer. In the previous lesson, you built a 3-input model on the regular season data. You can reuse this model to add predictions from the regular season model to the tournament dataset. This diagram shows the process for stacking these two models. You start with the regular season dataset and fit a model to it. You then predict on the tournament dataset using this model. This gives you predicted tournament outcomes, which you can now use to build a better model of the actual tournament outcomes. You additionally use the tournament seeds when modeling the tournament. These tournament seeds come from a committee and are intended to, like your model, capture each team's strength without using an embedding layer. The tournament seeds can be thought of as a simplified version of your team strength model, determined by a human rather than a computer. The prediction from the regular season model captures the effects of Team 1 and Team 2, which means you now don't need to use those two variables in the tournament model, and can avoid the use of an embedding layer. You can focus your modeling efforts on the purely numeric data, which is a little easier to work with. With purely numeric inputs, you can pass all of them to a single input layer. In other words, an input layer with a shape of 3 is another way of defining a 3-input model. The only drawback of this approach is that all the inputs must be numeric. A huge advantage of this approach is simplicity. You can create a model with a single input tensor and an output tensor and fit it using a single dataset. Similarly, evaluating the model requires a single dataset rather than a list. As you can see, this stacked model is pretty accurate. It's off, on average, by about 9 points in a given game. To recap, stacking Keras models means using the predictions from one model as an input to the second model. When stacking, it's important to use different data sets for each model. In this case, you use the regular season data for one model and the tournament data set for the second model. Finally, if your input data set is purely numeric, you can put multiple inputs in a single input layer. In this chapter, I will cover neural networks with two outputs. These sorts of networks make predictions for two targets at once. For example, you could use a single model to predict the scores of both teams in a basketball game, or use a single model to predict both the score difference and the win-loss outcome of that game. To me, this is the most interesting chapter in the class because it teaches you things that only neural networks can do. At the end of the chapter, I will show you how to make a single model that is both a classifier and a regressor. To create a model with two outputs, we start with an input layer, as with all Keras models. In this example, there is only one predictor, so I use an input layer with one input. To make a two-output model, I simply make a dense layer with 2 units for the output layer. The model will now make 2 predictions. Contrast this model with models from previous chapters, which all had single outputs, and therefore dense output layers with a single unit. The only difference between the 2-output model and the 1-output model is the size of the output layer. The API for creating a 2-output model and compiling it is exactly the same as for a single output model. Wrap the input and output tensors in your call to model, and then compile it using the Atom optimizer and mean absolute error. To fit a model with 2 outputs, you use a dataset with 2 columns for the y variable. In this case, the training set has the seed difference for the 2 teams, as well as the team's scores for the game. The model's single input is seed difference, and the 2 outputs are the scores for each team. The fit call is then exactly the same as a single input, single output model. The difference is that the y variable has 2 columns now. This particular model takes a while to converge, so I use 500 epochs in the fit. For the exercises, you will use some additional data in the model that will help it converge faster. Now that the model is fit, you can take a look at what it learned. The dense layer has 2 weights and 2 biases. The weights indicate that each additional unit of seed difference for the input data equals about 0.60 additional points for Team 1 and 0.60 fewer points for Team 2. The bias, or intercept term for each team is about 70 points, indicating that we expect an average basketball team to score about 70 points in an average game. In other words, 2 teams with a 1-point seed difference would be expected to have a score of about 69 to 71, while 2 teams with a 10-point seed difference would be expected to have a score of about 64 to 76. Evaluating a model with 2 outputs is very similar to evaluating a model with 1 output, except you provide the evaluation function a data set with 2 columns of data for the target. In this case, the model performs reasonably well in the test set, but in the exercises, you will add some more data to get better predictions. In this lesson, I will demonstrate how to build a simple model that performs both classification and regression. This is another example of a model with 2 outputs. In this case, however, rather than using 2 regression outputs, I have a regression output and a classification output. As before, I defined the regression part of this model with a single input and a dense output layer with a single unit. For the classification part of the model, I use the regression model prediction as input, and then add another dense output layer on top of it using the sigmoid activation, which will map the predicted score differences to probabilities that Team 1 wins. With 2 output models, each output needs its own loss function. For this model, I've specified 2 different loss functions, one for the regression model and one for the classification model. As with all the models in this course, I used Atom for the optimizer. To fit the combination classification regression model, you must provide the Y data as a list. Recall that this is similar to the way you built 2 input models in Chapter 2. Use seed difference as the only input to this model. For the regression output, I use score difference, and for the classification output, I use whether or not Team 1 won the game. I split both of these variables out from the training set and pass them to the fit method as a list. This model fits a bit more quickly than the last one, so I only use 100 epochs. This model's weight structure is a bit different from the last model, where both outputs were regression targets. The first layer has a weight of 1.24 and a bias of almost 0. This means that a 1-unit change in the team's seed difference yields about 1.24 additional points in their score difference. So two teams with a seed difference of 1 would be expected to have Team 1 win by 1.2 points. But two teams with a seed difference of 10 would be expected to have Team 1 win by 12 points. The next layer maps predicted score difference to predicted win-loss. Recall that the final layer in the model uses sigmoid activation. You can manually calculate the final layer in the model for some example data to get an understanding of how the model has learned to relate score difference to win probabilities. SciPy has a function called xpit, which is an efficient implementation of the sigmoid function. Let's manually calculate the win probability for two teams that are predicted to have a score difference of 1. First, multiply 1 by the weight for the final layer in the model, 0.14. Add the bias for the final layer, 0.0007. Since the bias is very close to 0, the result is still 0.14. Finally, we can apply the sigmoid function to 0.14, which yields a prediction of 0.54. In other words, the model has learned that an expected score difference of 1 point is equal to an expected win probability of 54%. Finally, you can evaluate the model on new data. First, split the evaluation dataset into a regression target and a classification target, and provide the same list of 2 targets to the evaluate method. This outputs 3 numbers now instead of 1 as with the models we looked at in other chapters. The first number is the loss function used by the model, which is the sum of all the output losses. The second number is the loss for the regression part of the model. And the third number is the loss for the classification part of the model. So our model has a mean absolute error of 9.28 and a log loss of 0.58, which is pretty good. But I think you can do better with more data when you try for yourself. In this course, I've tried to focus on designing network topologies that can be used to solve interesting problems. You learned how to build functional Keras models, including advanced topics such as shared layers, categorical embeddings, multiple inputs, and multiple outputs. You can now build a model capable of solving a regression and a classification problem simultaneously. In this final video, I'd like to discuss some real-world use cases of what you've learned. Shared layers are incredibly useful when you want to compare two things. For example, we compared 2 basketball teams to decide how different they were and their ability to score points in a basketball game, using a shared embedding model. In academic research, shared models are known as Siamese networks, which are used to calculate things like document similarity using a shared embedding layer and a shared long short-term memory layer, or LSTM layer, and then comparing the LSTM outputs. Since both documents are encoded with the same embedding layer and the same LSTM layer, the model learns a representation of the documents that can be used to compare them. Here are some links to further reading. Multiple input networks are especially useful when you want to process different types of data within your model. For example, in our basketball models, we process team IDs separately using an embedding layer. For numeric data, such as home versus away, we skipped the embedding step and passed it directly to the output. You can extend this concept to build a network that, for example, uses an LSTM to process text, a standard dense layer to process numerics, and a convolutional layer, or CNN, to process images. I didn't cover LSTMs or CNNs in this course, but once you understand them, you can use this concept to make networks that understand both text and images. The multiple output network you built in Chapter 4 is the coolest model of the course. It can do both classification and regression. I like this model a lot because the regression problem turns out to be a lot easier than the classification problem. In the regression problem, the neural network gets penalized less for random chance. For example, a team that wins by 1 point got really lucky, and the model can use that information. However, in the classification model, winning by 1 point is the same as winning by 10 points. I think it's pretty cool that we can use the output from the easier regression problem to help solve the more difficult classification problem. Here's a final example that we didn't explicitly cover in the class, but that is trivially easy now that you know how to use a concatenate layer. In a paper called Visualizing the Lost Landscape of Neural Nets, Lee et al. Propose a method called skip connections to simplify the optimization of neural networks. To summarize a very long and interesting paper, skip connections make it a lot easier for the ADAM optimizer to find the global minimum of the network's loss function. In Keras, implementing a skip connection is as simple as using the concatenate layer to concatenate the inputs to the deep network's outputs, right before the final output layer. I hope you enjoyed taking a deep dive into the Keras functional API with me, and that the flexibility of these neural networks will give you a lot of creative ways to solve your data science problems. Thank you for taking this course, and best of luck building deep neural networks.
Hello, my name is Ariel Rokem, and I am a data scientist. In this course, you will learn about convolutional neural networks, or CNNs. Imagine that you work for a company that is building a self-driving car. One of the challenges you face is that your car needs to quickly be able to determine what is happening around it. For example, your self-driving car should be able to tell whether the sign at an intersection is a stop sign or a yield sign. CNNs are powerful algorithms for processing images. In fact, these algorithms are currently the best algorithms we have for automated processing of images. And they are used by many different companies to do things like identifying the objects in an image. After completing this course, you will be able to build an algorithm that processes images of different objects and can distinguish between them. We will use Keras, which is a Python-based library that implements the building blocks you need to build your own CNNs. I assume that you have taken DataCamp's deep learning course, which introduces Keras. Because CNNs are a type of machine learning algorithm, I also assume that you have a working knowledge of basic principles of machine learning, such as overfitting and model evaluation through cross-validation. Images contain data. Using matplotlib, you can import an image into memory from a file and then display it using a plotting command, as shown here. But the computer doesn't see the image. All it sees is an array of numbers. Color images are stored in 3-dimensional arrays. The first 2 dimensions correspond to the height and width of the image, the number of pixels. The last dimension corresponds to the red, green, and blue colors present in each pixel. To examine the red, green, and blue data in a particular pixel in the image, we index into both of the spatial dimensions of the image. For example, when we index on both of the spatial dimensions, we can choose a pixel that is inside the stop sign by setting the row index to 1000 and the column index to 1500. This pixel has a high intensity in the red channel, so this is its color. On the other hand, the pixel with row index 250 and column index of 3500 is in the part of the image containing the sky and has a high intensity in the blue channel, so it has this color. We can also change the image by changing the array data. For example, Here we set the green and blue values of the pixels to 0. The result is an image that contains only the information in the red channel. Alternatively, we could set all the pixels within some part of the image to have no red and no blue, but full intensity in the green channel. This results in an image with a green square in it. In this course, we will mostly look at black and white images. For example, consider these 3 images of 3 different items of clothing: a dress, a t-shirt, and a shoe. What the computer sees are the numbers that represent the intensity of the image in each pixel. High numbers represent parts of the image that are brighter, and low numbers represent parts of the image that are darker. In these images as well, we can select a part of the image using indexing on the rows and columns of the array and slicing, and change part of the array using assignment. Next, let's consider what to do in order to classify images. We have images of 3 different classes: dresses, t-shirts, and shoes. We'd like to build an algorithm that can distinguish between these classes. In machine learning, this is called a classification task. In the training phase, we present the algorithm with samples from these 3 different classes, together with the class labels for each image. Over the course of training, the algorithm adjusts its parameters to learn the patterns in the data that distinguish between the 3 different classes of clothing. At the end of training, we would like to know how well our classifier does. To avoid an estimate that is overly optimistic because of overfitting, we evaluate it by testing it on a portion of the data that has been set aside in advance for this purpose. In this case, the classifier is able to correctly classify some of the images, but incorrectly classifies an image of a dress as a t-shirt, and an image of a t-shirt as a shoe. How do we represent data for classification? Consider the following series of labels. One mathematically convenient way of representing this data is called one-hot encoding. In this one-hot encoding array, each row represents one sample, and each column corresponds to one of the classes. In each row, all of the values are set to 0, except in the column corresponding to the class from which this image is taken. For example, here is a one-hot encoding of 3 images: a t-shirt, a dress, and a shoe. To generate a one-hot encoding of these samples, we generate an array of categories. We initialize an array of zeros, and then we iterate over the list of labels. For each sample, we find the index into the categories array that corresponds to the current sample. We set the item in the corresponding row and column to 1, and continue on to the next label until we have iterated over all labels. For example, we can use the one-hot encoded array to determine how many predictions were correct. In this case, we predicted 2 samples incorrectly out of 8 samples in the test set. The sum of the product of the 2 arrays is 6, which is the number of correct classifications. Let's use Keras to classify images. We'll start by using a fully connected network, like the one that you saw in the deep learning course. We start by importing the sequential model and initializing it. To construct our network, we will use densely connected layers. Every unit in every layer is connected to all the units in the previous layer. The first layer of the network is connected to all the pixels in the input image. The training data in this case are images of clothes, 50 samples, each of 28 by 28 pixels. The last dimension has length 1 because the images are black and white. 50 is a rather small number of training samples, but we'll use that here for simplicity, so that the training proceeds rapidly. The first layer is a set of densely connected units. We'll use 10 units here, but you could use another number. More units would increase the complexity of the network and its capacity to represent complex inputs. To facilitate learning, we're using a rectified linear unit, or ReLU, as the activation. This should be familiar from the deep learning course. The input shape keyword argument tells us how many inputs each of these units should expect. In this case, it is 784, one connection from each one of the pixels in the image. 28 by 28 is 784. We add another hidden layer, also with 10 units, also with the ReLU activation. The output of our network is a fully connected layer with a unit for each class of inputs. 3 classes for the 3 types of clothing. The output unit uses a Softmax activation to decide which of the 3 classes was presented. This diagram shows the network and all its connections. Next, we compile the model. We choose the optimizer to use, Atom, and a loss function, categorical cross entropy, which is appropriate for the classification task. Setting metrics to accuracy tells the model to report accuracy as well. The model expects samples to be rows in an array, and each column to represent a pixel in the image. So before we fit the model, we need to convert the images into a 2-dimensional table using the reshape method. We fit the model to training data. During training, the network adjusts its weights through backpropagation and gradient descent. We might go through the data several times until the network can accurately classify the images. Here, the model will run for 3 epochs, meaning that it will go over all of the training data 3 times. How do we know that the algorithm has reached a good set of weights? We worry that the algorithm might overfit to the training data. That is, that the weights result in very small error on the training set, but would not generalize well to another dataset. To avoid overfitting, we set aside a set of validation images. At the end of every epoch of training, we'll test the model on this validation set. Here, we use 20% of the images for validation by setting validation split to 0.2. This is the output. In each epoch, the program tracks progress through the dataset, and at the end of the epoch, prints the values of the loss function and the accuracy. Accuracy is still rather low because we used a small amount of data and we trained for only a few epochs. Another evaluation of the model should be done on a separate test set that was not used during training. This gives us a realistic separate evaluation of the model quality. Loss is 1.019 and accuracy is 40%. In the neural network that we previously constructed, each unit in the first layer had a weight connecting it separately with every pixel in the image. But we know that pixels in most images are not independent from their neighbors. For example, images of objects contain edges, and neighboring pixels along an edge tend to have similar patterns. How can we use these correlations to our advantage? Our own visual system uses these correlations, and each nerve cell in the visual areas in our brain responds to oriented edges at a particular location in the visual field. This image depicts a small part of the visual cortex. The scale par is 1 millimeter in size. Each part of the image responds to some part of the visual field and to the orientation depicted by the colors on the right. Looking for the same feature, such as a particular orientation, in every location in an image, is like a mathematical operation called a convolution. This is the fundamental operation that convolutional neural networks use to process images. Let's start with a simple version, a convolution in one dimension. We create here an array that contains 5 zeros followed by 5 ones. This array contains an edge in the middle where the values go from 0 to 1. The kernel defines the feature that we are looking for. In this case, we are looking for a change from small values on the left to large values on the right. We start the result as all zeros. Then we slide the kernel along the array. In each location, we multiply the values in the array with the values in the kernel and sum them up. This is the result for that location. In this example, the array goes between 0 and 1 twice. In this case, the edges that go from 0 to 1 match the kernel, but the edges from 1 to 0 are the opposite of the kernel. In these locations, the convolution becomes negative. Convolutions of images do the same operation, but in 2 dimensions. In this case, we convolve the image of a dress with a kernel that matches vertical edges on the left. This means that when we convolve the image with this kernel, the left edge is emphasized. The right side of the dress is the opposite of this kernel, and the convolution is negative there. Now, let's look at an implementation of convolution in code. First, we create the kernel. Then, we create the array that will store the results of the convolution. We iterate over all the locations in the image. In each location, we select a window that is the size of the kernel. We multiply that window with the kernel and then sum it up. This sum is then entered as the value of the convolved image in that location. At the end of the loop, the array will contain the results of the convolution. Here is a graphic that demonstrates the convolution operation. The kernel is the gray 3x3 box that slides over the blue input image at the bottom. In each location, the window is multiplied with the values in the kernel and added up to create the value of one of the pixels in the resulting green array at the top. In neural networks, we call this resulting array a feature map because it contains a map of the locations in the image that match the feature represented by this kernel. Keras has objects to represent convolution layers. Here, we have a 2-dimensional convolution that we can use to analyze images. It resembles the dense layers, but instead of having every unit in the layer connected to every unit in the previous layer, these connect to the previous layer through a convolution kernel. This means that the output of each unit in this layer is a convolution of a kernel over the image input. Here we have 10 convolution units. During training of a neural network that has convolutional layers, the kernels in each unit would be adjusted using backpropagation. The principle is the same as learning in the dense layers that we have seen so far, but with fewer weights. A dense layer has one weight for each pixel in the image, but a convolution layer has only one weight for each pixel in the kernel. For example, if we set the kernel size argument to 3, that means that the kernel of each unit has 9 pixels. If the layer has 10 units, it would have 90 parameters for these kernels. To build a network that contains a convolution layer, we need to import the sequential model, and we will need the dense as well as the conv2D layers. In addition to these layers, we will also need a flattened layer. This serves as a connector between convolution and densely connected layers. we initialize a sequential model and add a first convolution layer. In addition to the function arguments that I showed you before, the number of units, the kernel size, and the activation function, here we use the ReLU activation, we also add here the input shape. This is the size of each of the input images to the network. For example, for the images of clothing that we have been using, we might have image rows and image calls both equal to 28. To connect this layer to the next one, we add a flatten layer. This takes the output of the convolution that we previously referred to as a feature map and flattens it into a one-dimensional array. This is the expected input into the densely connected layer that is then added to the network as an output layer. Here, the output is one of 3 classes of clothing, so there are 3 units. To classify among the categories represented by the 3 units, we use the Softmax activation function. This is a diagram that describes the network that we created. The inputs are images of 28 by 28 pixels. The conv2d operation goes to 10 feature maps of 28 by 28 pixels each, and the flatten operation takes us to 3 units of the output. Just like before, the next step is to compile the model, choosing the optimizer and the loss function that we would like to use for fitting. For classification tasks, categorical cross-entropy is an appropriate loss function. We can also specify the metrics that we would like to see during training. Here, just the accuracy. Our training data are 50 samples of images of clothing. Each training item is a 28 by 28 pixel image with 1 channel. When we trained on a fully connected network, composed entirely of densely connected layers, we had to reshape this input before feeding it to the network. Here, we would like the pixels to retain their spatial relationships, so we don't do that. That is why we had to specify the input shape when we defined the convolutional layer. We fit the model with training data and training labels, after which we can test the accuracy of the model on a separate test dataset. Let's talk about the details of convolutions and how you might tweak them to do things slightly differently. This is an animation of a convolution that you have seen before. One thing that you might have noticed before is that the blue input image is larger than the green output image. This is because the convolution kernel has the size of 3 by 3 pixels. In this case, it converts a 3 by 3 window into 1 pixel in the output image. One way to deal with this issue is to zero pad the input image. Here's what that looks like. The dashed boxes around the central image are zeros that are added to the image. As you can see, when the input image is zero padded, the output feature map has the same size as the input. This can be useful if you want to build a network that has many layers. Otherwise, you might lose a pixel off the edge of the image in each subsequent layer. To implement zero padding in Keras, we will use the conv2d object's padding keyword argument. If we provide the value valid, no zero padding is added. This is also the default behavior. So if you don't specify padding, this is what you will get. On the other hand, if we provide the value same, zero padding will be applied to the input to this layer so that the output of the convolution has the same size as the input into the convolution. Another factor that affects the size of the output of a convolution is the size of the step that we take with the kernel between input pixels. This is called the size of the stride. For example, in this animation, the kernel is strided by 2 pixels in each step. This means again that the output size is smaller than the input size. Strides are also implemented as a keyword argument to the conv2d layers. The default is for the stride to be set to 1. This means that the kernel slides along the image and is multiplied and summed with each pixel location. If the stride is set to more than 1, the kernel jumps in steps of that number of pixels. This also means that the output will be smaller. For example, if the input image is 5 by 5 and there is both 0 padding and strides set to 2, the output will have a size of 3 by 3. Generally, we can calculate the size of the output using a simple formula: I minus k plus 2p divided by s plus 1, where I is the size of the input, k is the size of the kernel, p is the size of the 0 padding, and s is the stride. For example, if the input is 28 pixels, the kernel is 3 by 3, the padding is of 1, and the stride is 1, this number will be 28 minus 3 plus 2 divided by 1 plus 1 equals 28. If instead the stride is 3, the output size would be 10 by 10. Finally, you can also tweak the spacing between the pixels affected by the kernel. This is called a dilated convolution. In this case, the convolution kernel has only 9 parameters, but it has the same field of view as a kernel that would have the size 5 by 5. This is useful in cases where you need to aggregate information across multiple scales. This too is controlled through a keyword argument, dilation rate, that sets the distance between subsequent pixels. One of the major strengths of convolutional neural networks comes from building networks with multiple layers of convolutional filters. This is why using artificial neural networks is sometimes also called deep learning. This is the diagram that describes the network that we saw before. It has one convolutional layer, followed by a flattening, and readout with a fully connected layer with 3 units. And here is the code that implements this network. In this diagram, we have added one more convolutional layer. This layer also has 10 feature maps. Instead of operating directly on the image, the convolutions in this layer operate on each of the feature maps in the first convolutional layer. After the second layer, we again flatten the output of the convolutions and then pass on the flattened output to a 3-unit, fully connected layer that then provides the output of the network. Let's see how we might implement this. Here is the code for this network. First, we create the input layer. This is the same convolutional layer that we had in our previous network. Then, we add one more convolutional layer to the network. Because this layer receives its inputs from the first convolutional layer, it doesn't require the input shape keyword argument to be provided. Finally, we flatten the output of the second layer and pass it to a dense layer with Softmax activation to decide on the output. Why do we want to add additional layers to a network? This is again motivated by our own visual system, which has multiple layers of processing in it. For example, this is the architecture of a network developed by Google researchers in 2014. It has 22 layers of convolutions and some other kinds of layers, like pooling layers, that we will discuss in a subsequent lesson. For the time being, one way to understand why we would want a network this deep is by looking at the kinds of things that the kernels and feature maps in the different layers tend to respond to. For example, these are the kinds of things that layers in the early part of the network tend to respond to: oriented lines or simple textures. Intermediate layers of the network tend to respond to more complex features that include simple objects such as eyes. By the time the information travels up to higher layers of the network, the feature maps tend to extract specific types of objects. This allows the fully connected layers at the top of the network to extract useful information for object classification based on the responses of these layers. In other words, having multiple layers of convolutions in the network allows the network to gradually build up representations of objects in the images from simple features to more complex features and up to sensitivity to distinct categories of objects. How deep should your network be? Consider the following. Despite the advantages mentioned above, depth does come at a computational cost. In addition, to train a very deep network, you might need a larger amount of training data. When considering the architecture of networks, it is sometimes useful to think about the number of parameters in the network. Consider this dense two-layer network that processes images with 28 by 28 pixels. The first layer has 10 units. Each one of them is connected to each one of the pixels in the image through a weight. The second layer has 10 units, and each one of these is connected to all the units in the first layer. Finally, each one of the units in the last layer is connected to each of the units in layer 2. When you construct a Keras model, you can get a description of this model by calling the model's summary method. This tells us that the total number of parameters in the model is 7,993. The first layer has 7,850 parameters. That's one for every pixel in the image, 784 pixels, times the number of units in this layer, 10 units, plus 10 parameters for bias terms in every one of these units. In the second layer, there's one parameter for every unit in layer 1, times the number of units in this layer, plus 10 parameters for bias terms. The last layer has one parameter for every unit in layer 2, times the 3 units in this layer, plus 3 bias terms. That's why the total number of parameters is 7,993. And that's what the summary shows us here. What does that look like for a convolutional network with a similar number of units? Here is the code implementing a CNN with the same number of layers and units as our densely connected network. We run its summary method to find the number of parameters, which is 24,533. Let's do the math. In the first layer, there are 10 kernels with 9 parameters each, plus 10 bias terms. That's 100. In the second layer, each unit is connected through a convolutional kernel to each feature map in the first layer. That's 10 times 9 times 10 parameters, which is 900, and a bias term for each unit, which is a total of 910. The flattened layer has no parameters at all. It just takes the output from the feature maps in layer 2 and flattens them into one big array. Because there is zero padding here, the convolution leaves the same number of pixels in each subsequent layer, so we end up with 28 by 28 pixels in each feature map. With 10 feature maps, or 7,840 pixels in total, times 3 units in the last layer is 23,520, plus 3 bias terms is 23,523. Adding together, we get 24,533. So convolutional layers don't necessarily reduce the number of parameters. Let's look at another example. Here is a densely connected network with an increasing number of units in each layer. How many parameters does this network have? For this architecture, a lot of the parameters are concentrated at the first layer of the network, and then subsequent layers have much fewer parameters. This is the convolutional network with the equivalent number of units in each layer. In contrast to the densely connected neural network, when we run the summary method on this network, we see that the very first layers use very few parameters, while the last layer uses a lot of parameters. One way to think about this is that the convolutions have more expressive power, so they require less parameters. But reading out these more expressive representations then requires many more parameters on the output side. One of the challenges in fitting neural networks is the large number of parameters. One way to mitigate this is to summarize the output of convolutional layers in a concise manner. To do this, we can use pooling operations. For example, we might summarize a group of pixels based on its maximal value. This is called max pooling. In this image, we might start with the top left corner, extracting the pixels in this part of the image and calculating the maximal value of the pixels there. In the output, we replace these pixels with one large pixel that stores this maximal value. We shift our window and calculate the maximal value in the pixels in the next window, replacing that part of the image with one large pixel with the maximal value in that part of the image. If we repeat this operation in multiple windows of size 2 by 2, we end up with an image that has a quarter of the number of the original pixels and retains only the brightest feature in each part of the image. To understand this operation, let's see how to implement it. We start by allocating the output. This has half as many pixels on each dimension as the input. We start from the first coordinate in the output, calculating the maximum of the image in the first two coordinates on each dimension of the input. Next, we slide along the window by 2 pixels along the first dimension, calculating the maximum for this window. We keep going like that until we are done with the first row in the input. We then move the window to the beginning of the second row in the input, calculating the maximum for the coordinates in the third and fourth rows in the input for this location. We continue sliding the window along. Ultimately, in each location in the output, we calculate the maximum for a window of 2 by 2 pixels at the corresponding location in the input. Another way of implementing this operation is with a loop. In each iteration, we first select the corresponding rows. From the current row in the output, index II times 2, and until 2 pixels beyond that. And the same for the internal loop on the column index JJ. This performs the same operation that we previously broke down row by row. We can integrate max pooling operations into a Keras convolutional neural network using the max pool 2D object. After importing this object, in addition to the other objects we'll need, we start off building a convolutional neural network just like before. But after each convolutional layer, we'll add a pooling layer. The input to the max pool 2D object, 2 in this case, is the size of the pooling window. That means that here, pooling will take the max over a window of 2 by 2 pixels from the input for each location in the output. We add a second convolutional layer, followed by another max pooling layer. The summarization part of the network is the same as before, a flattening layer, followed by a dense layer with Softmax activation. How does this affect the number of parameters? Running the summary method for this model, we can see that using the pooling operation dramatically reduces the number of parameters in the model. Instead of more than 30,000 parameters that this model had with no pooling operations, we now have less than 2,000 parameters. There are, of course, trade-offs to reducing the number of parameters. During learning, the weights used by the network change. And as they change, the network becomes more attuned to the features of the images that discriminate between classes. This means that the loss function we use for training becomes smaller and smaller. Looking at the change in the loss with learning can be helpful to see whether learning is progressing as expected and whether the network has learned enough. As long as learning is progressing well, we might expect the loss function to keep going down. For example, here is a curve showing the categorical cross-entropy loss in a network that is learning to classify different types of clothing, measured on the training set. You can see that loss rapidly decreases in the first few epochs of training, after which learning slows down. This is a sign that learning is going rather well. On the other hand, if we add the validation loss to this plot, we can see that learning is progressing to some level of loss and then flattens out. What's going on? This is a form of overfitting. Because neural networks have so many parameters that can be adjusted, the weights can be adjusted to accurately classify, but this performance does not generalize well outside of the training set. When validated against a separate set of data, loss cannot become better. In fact, if we keep training for many epochs, the validation accuracy can start increasing back up again. This is a sign that we have passed the point at which the model weights are being adjusted in a useful way, and we are starting to overfit to the specifics of the training data. To generate these curves, we need a model like the ones that you've seen before. We capture the results of fitting our model into a training variable, which has a dictionary that stores the learning curves. We can plot the loss in the training set and also add a plot of the loss in the validation set. How do we use the best parameters before the network starts overfitting? By using the Callbacks module from Keras, which contain functions that can be executed at the end of each training epoch. One of these callbacks is a model checkpoint object that can be used to store the weights of a network at the end of each epoch of learning. When it is initialized, an HDF5 file is created. Here, we call it weights.hdf5. The callback monitors the validation loss and will only overwrite the weights whenever the validation loss shows improvement. That is, the validation loss decreases. This means that if the network overfits, the weights will be stored for the epoch at which the validation loss was the smallest before it started rising back up. The checkpoint object is stored in a list and passed as input to the model fitting procedure. After all epochs of fitting are done, this file contains the best weights. To use these weights, we'll need to initialize the model again with the same architecture, the same layers, with the same number of units in each. We can then use the model's load weights method to bring the model weights back to their value when the model was at its best during training. We can then use the weights in all kinds of ways. For example, we can use the model weights to predict the classes of a separate test image dataset using the predict classes method. Each entry in the result is the column corresponding to the clothing article in the one-hot encoded array. How do we prevent overfitting and make the best out of our training data? One of the strategies that has proven effective is regularization. Here, we'll discuss two strategies for regularization of convolutional neural networks. The first strategy is called dropout. In each step of learning, we choose a random subset of the units in a layer and we ignore it. This group of units would be ignored both on the forward pass through the network as well as in the backpropagation stage. Here is an image that explains this idea from the original paper by Nitish Srivastava and his colleagues that introduced this idea in 2014. On the left is a fully connected network, and on the right is this network with dropout applied to it during one step of training. This might sound strange, but this regularization strategy can work really well. This is because it allows us to train many different networks on different parts of the data. Each time, the network that is trained is randomly chosen from the full network. This way, if part of the network becomes too sensitive to some noise in the data, other parts will compensate for this because they haven't seen the samples with this noise. It also helps prevent different units in the network from becoming overly correlated in their activity. One way to think about this is that if one unit learns to prefer horizontal orientations, another unit would be trained to prefer vertical ones. In Keras, dropout is implemented as a layer. When we construct the network, we add a dropout layer after the layer for which we want units ignored. When using dropout, we'll need to choose what proportion of the units in the layer to ignore in each learning step. For example, here I have chosen to drop 25% of the units in the first layer. The rest of the model that follows is unchanged. Compiling and training the model is also unchanged. Another form of regularization in convolutional neural networks is called batch normalization. As the name suggests, this operation takes the output of a particular layer and rescales it so that it always has zero mean and standard deviation of 1 in every batch of training. This idea was proposed in a paper by Sergei Yoffe and Christian Zsekety in 2015. The algorithm solves the problem where different batches of input might produce wildly different distributions of outputs in any given layer in the network. Because the adjustments to the weights through backpropagation depend on the activation of the units in every step of learning, this means that the network may progress very slowly through training. Batch normalization is also implemented as another type of layer that can be added after each one of the layers whose output should be normalized. Here, I have added a single batch normalization operation after the first layer. The rest of the network is unchanged, and compiling and training the network would proceed as you have seen before. Finally, a word of warning. Sometimes dropout and batch normalization do not work well together. This is because while dropout slows down learning, making it more incremental and careful, batch normalization tends to make learning go faster. Their effects together may in fact counter each other, and networks sometimes perform worse when both of these methods are used together than they would if neither were used. This has been called the disharmony of batch normalization and dropout. One of the main criticisms of convolutional neural networks is that they are black boxes, and that even when they work very well, it is hard to understand why they work so well. Many efforts are being made to improve the interpretability of neural networks, and this field is likely to evolve rapidly in the next few years. One of the major thrusts of this evolution is that people are interested in visualizing what different parts of the network are doing. Here, I will show you how to take apart a trained convolutional network, select particular parts of the network, and analyze their behavior. Once a model is constructed and compiled, it will store its layers in an attribute called layers. This is a list of layer objects. For example, here is a network with 2 convolutional layers followed by a flattening operation and readout with a dense layer. If we want to look at the first convolutional layer, we can pull it out by indexing the first item in this list. The weights for this layer are accessible through the getWeights method. This method returns a list with 2 items. The first item in this list is an array that holds the values of the weights for the convolutional kernels for this layer. The kernels array has the shape 3 by 3 by 1 by 5. The first 2 dimensions denote the kernel size. This network was initialized with a kernel size of 3. The third dimension denotes the number of channels in the kernels. This is 1 because the network was looking at black and white data. The last dimension denotes the number of kernels in this layer, 5. To pull out the first kernel in this layer, we would use the index 0 into the last dimension. Because there is only 1 channel, we can also index on the channel dimension to collapse that dimension. This would return the 3 by 3 array containing this convolutional kernel. We can then visualize this kernel directly, but understanding what kinds of features this kernel is responding to may be hard just from direct observation. To understand what this kernel does, it might sometimes be even more useful to convolve one of the images from our test set with this kernel and see what aspects of the image are emphasized by this kernel. Here, we pick the 4th image from the test set, an image of a shoe. We convolve it with the kernel using the function that we created previously, and create a filtered image that is the result of this convolution. This filter seems to like the external edges of this image on the left. We can confirm this by running the convolution over another image. Here we've picked the 5th image from the set, an image of a t-shirt. We see that here as well, vertical edges on the left side of the object are emphasized, and on the right side are de-emphasized. We can do the same thing with another one of our kernels. Here we select the 2nd kernel and convolve the t-shirt image with this kernel. This kernel seems to have learned to detect horizontal edges, particularly on the bottom of the object. Taken together, this gives us an intuition for the kinds of things that the first layer of the network has learned, and can help interpreting the results you see from using this network for a particular task. Congratulations! You have completed this course on image processing with convolutional neural networks. These algorithms are the best we currently have for many computational tasks. Here, you learned about image classification. Classification is a particularly useful task and one that convolutional neural networks excel at. You learned how to set up a training set, a validation set, and a test set, and how to use them in training a model for classification, and how to evaluate it. You learned about the fundamental operations of these networks, convolutions. The development of convolutional layers for neural networks ushered in the current golden age of computation with neural networks. So understanding how they work is particularly valuable, even if you continue to learn about other kinds of neural networks. One of the things that is remarkable about CNNs is that they have a very large number of parameters. This is one of the reasons that large amounts of data are usually required to effectively and accurately train a neural network. We looked at a couple of approaches to reduce the number of parameters. One is to tweak your convolutions and adapt them to your problem. For example, using strided convolutions. Another approach is to use pooling layers. We also looked at a couple of approaches to improve your network using regularization. Finally, you learned about ways to understand your network and visualize both the progress of learning as well as the final result of learning, the parameters of the trained network. If you found this topic to be interesting, you might want to read this paper by Chris Olah and his colleagues that explores different aspects of visualization of neural network results. This is an exciting time to learn about CNNs because the technology is rapidly evolving and some of the most exciting developments are yet to come. Where does the road lead to from here? There is a wealth of methods and ideas for you to dive into. Here are a few things to learn about next. In this course, you learned about simple architectures, where one layer always connects only to the next. But there are other architectures that provide a variety of computational benefits. For example, you might want to learn about residual networks. These include connections that skip over several layers, and they are called residual networks because the network will use this skipped connection to compute a difference between the input of a stack of layers and their output. Learning this difference, or residual, turns out to often be easier than learning the output. This means that these networks have been surprisingly effective at tasks such as classification. Another topic you might want to explore further is transfer learning. In this approach, an already trained network is adapted to a new task. You've already learned how to read in weights into a network that you've defined. Now imagine training it again on another classification task. Sounds weird, but it's a great strategy for cases where you don't have a lot of data. In addition to convolutional networks that perform classification, there are so-called fully convolutional networks that take an image as input and produce another image as output. For example, these networks can be used to find the part of an image that contains a particular kind of object, doing segmentation rather than classification. A particularly interesting kind of networks are generative adversarial networks. These complex architectures can be used to train a network to create new images that didn't exist before. And there are many other topics to explore. Whichever way you decide to turn next, good luck.
Hi, my name is David. I'm a data scientist that focuses on text data for real-world applications, and I'm proud to be your instructor for this course, where you will be introduced to 4 different applications of language models using recurrent neural networks with Python. So, why learn to model language or text data? Well, we know that data science models require data to be effective, and one kind of data that is available on the internet is text. From news articles to tweets, the volume of text data is increasing fast and is freely accessible to anyone with an internet connection. So, what can data scientists do with all this data? In this course, you will introduce 4 applications: sentiment analysis, multi-class classification, text generation, and machine neural translation. In the next slides, we will define each of these applications. If you have an online customer interaction, you may be interested in knowing how your customers feel towards your brand or product. To do that, you can use sentiment analysis models and classify their messages into positive or negative. Or you want to build a recommender system and need to categorize news articles into a set of predefined categories. Also, it is possible to generate text automatically using a specific writing style, or automatically reply to messages. Lastly, it is also possible to create models that translate from one language to another. All these applications are possible with a type of deep learning architecture called recurrent neural networks. So what is different about RNN architectures and why do we use it? The main advantages to use RNN for text data is that it reduces the number of parameters of the model by avoiding one-hot encoding, and it shares weights between different positions of the text. In the example, the model uses information from all the words to predict if the movie review was good or not. RNN's model sequence data and can have different lengths of inputs and outputs. Many inputs to one output is commonly used for classification tasks, where the final output is a probability distribution. This is used on sentiment analysis and multi-class classification applications. Many inputs to many outputs for text generation start the same as in the classification case, but for the outputs, it uses the previous prediction as input to the next prediction. Many inputs to many outputs for neural machine translation is separated in two blocks, encoder and decoder. The encoder learns the characteristics of the input language, while the decoder learns for the output language. The encoder has no prediction, no arrows going up, and the decoder doesn't receive inputs, no arrows from below. Many inputs to many outputs for language models starts with an artificial zero input, and then for every input word I, the model tries to predict the next word I plus 1. In this lesson, you will learn in more detail how to create a language model from raw text data. Language models represent the probability of a sentence. For example, what is the probability of the sentence, "I love this movie"? What is the probability of each word in the sentence to appear in this particular order? The way this probability is computed changes from one model to another. Unigram models use the probability of each word inside the document and assume the probabilities are independent. N-gram models use the probability of each word conditional to the previous n-1 words. When n equals to 2, it's called bigram, and when it's equal to 3, it's called trigram. The skipgram model does the opposite, computes the probability of the context words or neighboring words, given the center word. Neural networks models with a softmax function in the last layer of the model, with units equal to the size of the vocabulary, are also language models. When focusing on recurrent neural networks, so how exactly are language models related to them? Well, everywhere. Recurrent neural networks models are themselves language models when trained on text data, because they give the probability of the next token given the previous k tokens. Also, an embedding layer can be used to create vector representations of the tokens as the first layer. When creating RNN models, we need to transform the text data into a sequence of numbers, which are the indexes of the tokens in the array of unique tokens, the vocabulary. To do that, we first need to create an array containing each unique word of the corpus. We can use the combination list-set to create a list of unique words. And we can get all words in the text by splitting the text using space as the separator. Other languages, such as Chinese, need additional steps to get words, since there is no space between the characters. We can now create dictionaries that map words to their index on the vocabulary and vice versa using dictionary comprehension. By enumerating a list, we obtain the numeric indexes and the items as tuples, and we can use them to create key-value dictionaries. The first dictionary uses the words as keys and the indexes as values. It can transform the text into numerical values. The later one is used to go back from numbers to words, since it has indexes as keys and words as values. With the created dictionaries, we can prepare pairs of X and Y to be used on a supervised machine learning model. For that, we can loop into the sequences of numerical indexes in blocks of fixed length size. We use the initial words as X and the final word as Y, and shift the text stepwards forward. If we use a step equal to 2, it means that the X sentences will be shifted by 2 words at a time. When preparing new data, we can use the dictionary to get the correct indexes for each word. Using the example on the slide, create a list that will contain the transformed text. Loop for every sentence of the new text. Create a temporary list that will contain the current sentence. Iterate over all words of the sentence by splitting the sentence on its white spaces. Get the index using the dictionary. Append the index to the sentence list. Then, append the sentence of indexes on the first list you created, the new text split. You saw the language models give the probability of a sentence. To train the model, you first need to prepare the raw text. In this lesson, we implement the RNN models using Keras. Previously, you were introduced to the architecture of language models. Now, we will use Keras to create and train RNN models. Keras is a high-level API with deep learning frameworks as background. It is possible to configure Keras with TensorFlow, CNTK, or Theano. To install Keras, we can simply use the Python Package Manager, PIP. After installation, we can use its modules to execute fast experimentation and research. Next, we will introduce the main modules of Keras that will be useful for the language models. Keras models contains 2 classes of models. The sequential class has a structure where each layer is implemented one after the other, meaning that the output of one layer is the input of the next one. The model class is a generic definition of a model that is more flexible and allows multiple inputs and outputs. Keras layers contains the different types of layers, including the LSTM and GRU cells. Other layers that we will use are dense, dropout, embedding, and bidirectional. Keras preprocessing contains useful functions for pre-processing the data, such as the pad sequences method that transforms text data into fixed-length vectors. In the example, we padded the text to equal length of 3. The datasets module contains useful datasets. For example, the IMDb movie reviews that is used for sentiment analysis. Also, the Reuters Newswire dataset used for topic classification with 46 classes. There are also other datasets that you can check on the Keras website. You can build a sequential model in Keras with just a few lines of code. Import the required classes as From keras.models, import sequential. From keras.layers, import dense. Then instantiate the class in the variable called model with model equals to sequential open and close parentheses. Add desired layers with the method add as in model.add dense 64 activation equals to the string reload. Input dim equals to 100. The parameter input dim declares the shape of the input data, which is mandatory for the first layer in the model. Then add the output layer model.add dense 1 activation equal to the string sigmoid. Finally, we can compile the model by executing the compile method of the class. We pass the string Adam to the optimizer parameter, the string mean squared error to loss, and a single element list containing the string accuracy to the matrix parameter. To train the model, we use the fit method on the training data. For example, model.fit xtrain ytrain epochs equals to 10, batch size equal to 32. Epochs is the number of iterations over the entire dataset and defaults to 1. Batch size is the size of a subset of the data that will be used on each step. When the dataset cannot fit in the memory, this is crucial. It defaults to 32. To analyze the model's performance, we can use the method evaluate as model.evaluate xtest, ytest. This method returns the loss and accuracy values. To use the model on new data, use the method predict as model.predict new data. To create a full example, let's instantiate the sequential class. Add 3 layers. Don't bother with the new layers for now. We will explain them in details on chapter 2. And compile. Next, we can use the training set to fit the model and measure its accuracy on the test set. You learned the main modules present in Keras and how to create, evaluate, and use the model. You learned how to prepare text documents and use them on a RNN model to classify sentiment on movie reviews. But the accuracy was not as expected. In this lesson, you will be introduced to some pitfalls of vanilla RNN cells, which are the vanishing or exploding gradient problems, and how to deal with them. To understand the vanishing or exploding gradient problems, you first need to understand how the RNN model is trained. In other words, how to perform backpropagation. In this picture, you can see the forward propagation and backpropagation directions. The important part here is that they follow 2 directions, vertical between input and output, and horizontal going through time. Because of this horizontal direction, backpropagation is referred as backpropagation through time. In the forward propagation phase, we compute a hidden state A that will carry past information by applying the linear combination over the previous step and the current input. The output Y is computed only in the last hidden state, often by applying a sigmoid or softmax activation function. The loss function can be the cross-entropy function, and we use it to have a numeric value of the error. We can see that the past information is carried out during the forward propagation with an example. The second step combines the results from the first step and receive the second word as input. We can also see that the weight matrix WA is used on all steps, which means the weights are shared among all the inputs. In the backpropagation phase, we have to compute the derivatives of the loss function with respect to the parameters. To compute the derivative of the loss with respect to the matrix WA, we need to use the chain rule because y hat depends on AT, which also depends on WA. But AT also depends on AT minus 1, that depends on WA. Thus, we need to consider the contribution of every previous step by summing up their derivatives with respect to the matrix WA. Also, the derivative of AT with respect to WA also need the chain rule of derivatives and can be written as the product of the intermediate states multiplied by the derivative of the first state with respect to the matrix. Not going into too much detail on the math, when computing the gradients of the loss function with respect to the weight matrix, we obtain the matrix WA power t minus 1 multiplied by a term. Intuitively, if the values of the matrix are below 1, the series will converge to 0, and if its values are above 1, it will diverge to infinity. Researchers found some approaches to avoid those problems. Limiting the size of the gradients or scaling them can easily help us avoid the exploding gradient problem. Initializing the matrix W as an orthogonal matrix makes their multiplication always be equal to 1. Using regularization controls the size of the entries. By using the ReLU activation function, the derivative becomes a constant and thus doesn't increase or decrease exponentially. Finally, use other RNN cells such as GRU and LSTM that we will learn later. You learned about the vanishing or exploding gradient problem. In this lesson, you will learn about two different RNN cells that will achieve good results in language modeling and solve the vanishing gradient problem. Let's first have a detailed look on the simple RNN cell. On every cell, we compute the new memory state based on the previous memory state t-1 and the current input word xt. In the computations, we have a weight matrix WA that is shared between all steps. We will consider the case of classification tasks and thus the output y hat will be computed only in the last step. GRU cells were proposed in 2014 and add one gate to the vanilla RNN cell. Now, before updating the memory cell, we first compute a candidate A tilde that will carry the present information. Then, we compute the update gate GU that will determine if the candidate A tilde will be used as memory state or if we keep the past memory state A-1. If the gate is 0, the network keeps the previous hidden state, and if it's equal to 1, it uses the new value of A tilde. Other values will be a combination of the previous and the candidate memory state, but during training, it tends to get close to 0 or 1. LSTM was first proposed in 1997 and adds 3 gates to the vanilla RNN cell. The forget gate, GF, determines if the previous state CT-1 state should be forgotten, meaning to have its value set to 0 or not. The update gate, GU, do the same for the candidate hidden state C tilde. The output gate, GO, do the same for the new hidden state CT. The green circles in the picture represent the gates. We can think of them as an open or closed gate, allowing for the left side to pass through or not, if the gate values are 0 or 1 respectively. Because GRU and LSTM cells add gates to the equations, the gradients are no longer only dependent on the memory cell state. The derivative of the loss function with respect to the weights matrix depends on all the gates and on the memory cell, summing each of its parts. Without going into deeper details on the math, this architecture adds the different gradients corresponding to the gradients of each gate and the memory state, making the total gradient stop converging to 0 or diverging. On every step, if the gradient is exponentially increasing or decreasing, we expect the training phase to adjust the value of the corresponding gate accordingly to stop this vanishing or exploding tendency. Without further discussing the intuition and the theory, let's put the new RNN cells in practice inside Keras. First, the layers with the GRU and LSTM cells are available in the keras.layers.recurrent with a shortcut on keras.layers. To use the GRU and LSTM cells on a Keras model, we simply add them as usual. The important parameters are the number of units, meaning the number of memory cells to keep track, and the return sequences parameter, that is used when adding more than one layer in sequence, making all the cells to emit an output that will be fed to the next layer as input. Now that you understand how to differentiate the RNN cells, you will learn now about vectorization of a language model using the embedding layer in Keras, and how it can be used for transfer learning. The first reason to use embeddings is because the one-hot encoding of the tokens in a scenario with a very big vocabulary, maybe 100,000 words, demands a lot of memory. An embedding layer with dimension, say 300, is more viable. Also, embeddings are a dense representation of the words, and the implementations give surprisingly nice understanding of the tokens, like the famous king minus man plus woman equals to queen. Finally, it can be used for transfer learning. On the other hand, it demands training lots of parameters to learn this representation and can make training slower. To use the embedding layer in Keras, we first import it from keras.layers module. The embedding layer should be the first layer of the model. The relevant parameters include input dim, which is the size of the vocabulary, output dim, which is the dimension of the embedding space, trainable, that defines if this layer should have its weights updated or not during the training phase, embedding initializer, that can be used to perform transfer learning by using pre-trained weights for the words in your vocabulary. Often, when using transfer learning, we set trainable to false, but it's not mandatory. The final parameter is the input length, which determines the size of the sequences. It assumes that you padded the input sentences beforehand. There are many pre-trained vectors that were trained on big datasets such as the Wikipedia, news articles, etc. To train a model on those big sets demand a lot of computer power, but loading the weights does not. Recent advances in NLP and language models research is based on open sourcing pre-trained weights on big datasets using popular models such as Glove, Word2Vec, and BERT, among others. In Keras, we need to constant initializer to define the pre-trained matrix of the embedding layer. Globe files contain rows separated by spaces, where the first column is the word and the others are the weights values for each dimension of the embedding space. To read the values, then, we loop over the rows of the file. Split the line by spaces. Get the word as the first item of the list, and the rest of the list are the weights. We use dictionaries to easily store for each word an NP array with the values. We also cast the values to have float 32 type because it is the type used to create the vectors. To use the globe vectors in a specific task, we can simply select the words present on the vocabulary list, ignoring the other words, to save memory. We need the task-specific vocabulary dictionary with words as keys and indexes as values, the globe dict created in the previous slide, and the dimension of the embedding space as inputs. We define a matrix with shape equal to the number of words plus 1 and the embedding space dim. We add 1 because the index 0 is reserved for the padding token. We iterate over the vocabulary words. If the word is found in the globe vectors, then we update this row of the matrix with the values from globe. You learned about different RNN architectures, such as GRU and LSTM, and also about the embedding layer. Those are the first steps to tune a RNN model and improve performance. Let's put it all together to form a better model. In the first chapter of this course, you implemented a simple RNN model to classify sentiment on the IMDb dataset. But the performance was really poor and achieved less than 50% accuracy. You learned some approaches to improve the model's performance. In summary, we can add the embedding layer, increase the number of layers, tune the parameters, increase the vocabulary size, accept longer sentences with more memory cells. RNN models can overfit even with a few epochs like 10. If the model overfits, we can test using different batch sizes because RNN models are very sensitive to them, since the batch size determines the number of updates in the weights that will be performed. Also, adding dropout layers and using the parameters dropout, recurrent dropout can add extra noise to the training data, forcing the model to be more general and reduce overfitting. The parameter dropout on RNN layers removes a percentage of the input data, while the recurrent dropout removes a percentage of the memory cell. Despite not being in the scope of this course, the mix of convolution and max pooling layers with RNN cells has been used recently and achieved state-of-the-art results in NLP problems. In short, the convolution layers has filters that determines the output dimension, kernel size, which is the window size for convolution, and padding, which determines if the input should be padded, add zeros around the matrix or not. The max pooling contains the parameter pool size that determines the window to look for the max value. For more details on convolution and max pooling layers, search for convolution courses on DataCamp. We created a model after some iterations of tests and parameter tuning to obtain high accuracy on the sentiment classification task. The model architecture is using the embedding layer in the first layer of the model. Add a dense layer. Add one LSTM layer. Add one GRU layer. Add two other dense layers. Add another dense with one unit as output layer. The dropout layers are to avoid overfitting by adding extra noise to the data, by removing some of the inputs. You saw that it is possible to play with the models, add new layers, change parameters, etc. The art of creating the best possible model demands experience and deep understanding of the parameters. You learned before how to perform sentiment analysis on the IMDb dataset. Sentiment analysis was framed as a classification problem with two classes. Let's learn now when there are more than two classes. Text classification can be applied to many different problems. Historically, it is studied as news articles classification into a predetermined set of classes. And based on the summary or the title or even the whole body of the article, the machine learning models determine if the news article is about economy, sports, real estate, and so on. It can also be used for classifying a company's documents into categories that will be analyzed only by the corresponding department. Finally, it can direct, for example, an online customer service representative to the specific problem by classifying the query that the customer wrote when contacting the service, allowing to solve the problem faster and increasing customer satisfaction. A few parameters change when going from binary to multi-class classification, the most notable ones being the shape of the variable y containing the classes, the number of units on the output layer, the activation function to use on the output layer, and the loss function. The shape of the variable y changes with the application of the one-hot encoding. Thus, the output layer also needs the number of classes as units. One-hot encoding makes all the classes to be equidistant. If we use numbers as representation for three different classes, it would imply that class 1 is closer to class 2 than it is to class 3, and in many applications this is not the case. Also, during the training of the model, the loss function will show bigger error if misclassified class 1 as class 3 than if it misclassified class 1 as class 2, and this is an error. Using one-hot, all the classes will have a distance equal to 1. Furthermore, the Softmax function will return the probability of each class, and we can easily assign the document to the class that has higher probability, and the loss function will work as expected. The same goes for the activation function. The sigmoid function is very useful and fast to separate two classes, but when we have more than two, it is not recommended. Instead, we use the Softmax function that gives the probability of each class given the inputs, and we can choose the one with higher probability. Finally, we were using the binary cross-entropy activation function, but now we have more than two classes, and it is more appropriate to use the corresponding version called categorical cross-entropy. Sometimes our data uses text to represent the classes. Then, we can use Panda series category data types to transform text into numbers by accessing its cat.codes attribute. This is the first step for preparing the data. The second step is to transform y into one-hot encoded values using the function toCategorical from keras.utils.nputils. We simply apply it to the numeric vector of classes representation to obtain the one-hot encoded version of the vector. In the last chapter, you were introduced to transfer learning for language models using Glove. Now, let's have a closer look on the different available word embeddings that can be used for transfer learning. Depending on the problem at hand, different ways to treat text can improve the model's quality. Transfer learning became popular initially for computer vision tasks. Later, it was also applied to language models. Transfer learning provides a model with a better initialization values, meaning that instead of initializing the weights all equal to 0 or with random numbers, we use the values obtained previously in a similar task. In other words, we use knowledge already available. Some research institutes and companies started to use their computer power availability to train models on very big datasets and share the obtained weights with the community. Glove is an example of this. We were able to use the weights of the Glove vectors trained on the whole Wikipedia data, task that would be impossible with limited computer power. This allows many more researchers to improve the current knowledge in many fields by using those shared weights as a starting point and evolving from there. Researchers with limited computer power could achieve state-of-the-art results because of this open sourcing of the models. There are a few alternatives to Glove models. Word2Vec was created in 2013 by Google and contains two approaches to model a corpus: the continuous bag of words model and the skip-grant model. Continuous bag of words uses neighboring or context words to predict the center word, while the skip-grant model does the opposite, which is to utilize the center word to predict its context words. Fast text was created by Facebook in 2016 as an improvement of the Word2Vec model. It uses a word and n-grams of its chars to train the model. Finally, Elmo was created by Allen Institute in 2018 and achieved state-of-the-art in many NLP tasks. It uses words and bidirectional layers to train the language model. Word2Vec and fast text are available in the package GenSim, while Elmo is available on TensorFlow Hub. Elmo is out of the scope of this course. To use Word2Vec in Python, import the Word2Vec class from gensim.models. To train a model, we initialize the subclass Word2Vec passing a corpus. Other parameters include size, which is the dimension of the embedding vector to use, window, which is the number of neighbor words to use as context, and iter, which is the number of epochs to train the model. We can use the model, for example, to find similar words in the corpus. For that, we access the word vectors attribute wv and the method mostSimilar, passing a list of words to find similarities and the number of similar words to retrieve. Same as Word2Vec, fast text is also implemented in GenSim and does share many attributes and methods. We first import the class fastText from GenSim. Then, to train a model, we have 3 steps. First, we instantiate the model with basic parameters like the size of the embedding vector and the window containing the number of neighbor words to use as context. Then, we build the vocabulary based on the corpus. Finally, we train the model by passing the corpus, the total number of documents or sentences in the corpus, and the number of epochs to train. The same methods, such as finding similar words, are also available on the fastText class. Now you are going to build models in Keras and see how to perform multi-class classification. Let's dive in. In the first chapter, you learned to build a sentiment classification model using Keras. The model was created using the Sequential class, the embedding layer, one LSTM layer and the output layer with the sigmoid as the activation function. We compiled the model using binary cross-entropy loss function, the Adam optimizer, and accuracy as metric. The same architecture used for sentiment classification can be used for multi-class classification. The only difference, as mentioned before, is that the last layer now has the number of classes units and uses Softmax as activation function. Also, when compiling, we use the categorical cross-entropy loss function. To implement multi-class classification, we are going to use the 20 news groups dataset. The dataset is available in sklearn by the function fetch 20 news group contained in sklearn.datasets module. We can download the train and test data separately by using the parameter subset as in newsTrain equal to fetch 20 news groups subset equal to string train. Same goes to download the test set. The fetched data has the following attributes. .descr contains the documentation of the dataset, including examples of usage. .data is an array containing the text of each news article. .filenames contains an array with the file names on disk. .target contains an array with the numerical index of the true class of each news article. .target names is an array with the unique names of the classes. We will use the raw text of the 20 news groups dataset, so you can apply the same steps on any other dataset you are interested in. To pre-process the text, we will use the tokenizer class from keras.preprocessing.text module and the pad sequences function from keras.preprocessing.sequence module. To pre-process the targets, we will use the function toCategorical as before. The tokenizer class would create numerical indexes of the vocabulary present on the training data, so we can use on our RNN models. We first instantiate the class and keep it on the variable tokenizer. Then we use the method tokenizer.fit on texts and pass the new strain.data as the array to fit on. This updates the tokenizer instance with the vocabulary and indexes. Next, we transform the text data into a sequence of numerical indexes using the tokenizer.textToSequences method and apply on the new strain.data. Save the results in the xtrain variable. Now, we pad the sequence for them to have the same length using the pad sequences function. We use maxlen equal to 400 as an example. This value should be big enough not to cut too much of the text and small enough to limit the size of the data. If the texts have similar lengths, for example tweets, you can use the maximum length of your sample as the value, for example 200. Finally, we change the targets into a one-hot encoded matrix using the function toCategorical, passing the new strain.target. Having pre-processed the data, we can use it on the Keras model to train it. We can also evaluate the performance of the model in a test set. You learned how to build multi-class classification models in Keras. Now we will see how to calculate the model's performance. Imagine that you built a model and achieved 80% accuracy on the test data. Is this model good? Can you say if the model is classifying all the classes correctly? Or if the accuracy is the same for each class, or if the model is predicting only the class with more observations and thus achieving high accuracy. We cannot say looking only on the accuracy. In the confusion matrix above, we have the predictions on the columns and the true labels on the rows. The numbers represent the frequencies of prediction or true labels in each of the classes. The total number of observations is 100. We can see that the model has 80% accuracy by summing the diagonal of the matrix that corresponds to the corrected prediction of each class. Psi.space, out.autism, and soc.religion.christian. But we can see that the model predicts almost always the class psi.space. This model is overfitted to this class and has poor performance on the others. How can we make a better metric? One possible metric is the precision. It measures for each class if the model is accurately predicting this class. Another is the recall that measures if the classes are being correctly classified. F1 score is an weighted harmonic average between precision and recall. We can compute the confusion matrix using a function called confusion_matrix from sklearn.matrix. The function receives two parameters, yTrue and yPred, containing the correct and predicted values. We can see from the output that the model seems to have higher accuracy for the first class. Now, let's see how to compute the performance metrics with Python. We will use the implementation in sklearn to compute the metrics. The performance metrics can be found in the sklearn.matrix module, and we can import the confusion matrix, precision score, recall score, F1 score, accuracy score, and classification report. The accuracy score gives the overall performance of the model. To use the other functions, we should pass the parameter average equal to none. Will be explained later. We can check the values of the matrix to see that they change greatly from class to class. F1 score of 0.15 and 0.35 for the second and third classes is not a good performance. All those metrics can be computed in one function, the classification report. This function can receive the parameter target names with the classes names for better print. The output is a formatted string with precision, recall, F1 score, and support for each class. Support is the number of observations of the class present on the data. At the end, it also shows values for microaverage, macroaverage, and weighted average. Microaverage is an average between true positive, false positive, and false negative rates and is one value for all classes. Macroaverage computes the average of precision, recall, and F1 score between all labels, and weighted average is the average weighted by support. This is the last chapter of this course, and also the most challenging. You will learn about sequence-to-sequence models and applications to text generation by creating a model that generates sentences based on the Big Bang Theory character Sheldon, and neural machine translation by creating a model to translate small sentences from Portuguese into English. Sequence-to-sequence models can be divided in two groups, the ones with one output, which we saw when doing sentiment analysis and multi-class classification, and the one with many outputs, which is the object of study in this chapter. It contemplates text generation and neural machine translation. Text generation is the process of automatically creating textual content. State-of-the-art models perform so well that a person cannot identify that the text was created by a machine. In the model above, we can see that some words are not correct and can easily identify that it was generated by a machine. A text generation model should go through the same process as before. First, though, you need to choose if your token will be characters or words. If you choose words, then you will need a very large dataset to predict on the big size of the vocabulary. If you choose chars, then the size of the vocabulary will be much smaller because we have 26 letters on the alphabet, plus some other punctuation. Then, you need to prepare the data for training. That means to create vectors of past tokens and next token. The next step is to design the architecture of the model, choosing to use an embedding layer, how many RNN layers, and so on. Finally, train the model, see the outcome and make adjustments. Neural machine translation is the process to automatically translate one language to another. It is used, for example, on Google Translator. The model above was trained to translate small phrases, such as this example with 3 words, but it becomes much more complex to train models that can translate a whole paragraph, or an entire page, or even a full document. Since the text would be bigger, we would need more units on the RNN cell, meaning more memory cells to keep longer dependencies. Thus, it will be a much bigger model, need more data and time to train. The NNT model is similar to the text generation model, but it has to deal with 2 languages at the same time. To acquire training data, we can search for open source projects such as the Anki. In the data preparation phase, we need to tokenize the 2 languages. It is also possible to use characters or words as tokens, but words are used more often. Then we have to design the model to be used, and is separated in 2 parts, the encoder and the decoder. More details will be given further in this course. Again, as in all machine learning projects, you need to experiment and evaluate the results, then make adjustments as needed. In this chapter, you will learn in more details about text generation and neural machine translation models. First, you will learn how to use a pre-trained text generation model to generate sentences. Then, you will learn how to prepare the data and build the Keras model for this task. Finally, you will do both steps for neural machine translation. Prepare the data, build a model, and use it to translate Portuguese to English. In this lesson, we are going to focus on how to generate phrases or custom text given a trained model. In some applications, we want to generate only one sentence, while in others, we may be interested in a whole paragraph, an entire book even. So, let's see how to create rules for the generated text. To generate sentences, we need first to define what is a sentence so that we can create rules to generate them. One definition is to use punctuation to determine when the sentence ends. For example, we can use period, exclamation, or question marks. If we use this approach, we must make sure that those punctuations are present in the vocabulary. Another definition is to use special tokens for the beginning and end of a sentence. For example, use token sent to start the sentence and /sent to represent its end. This approach needs the training data to be pre-processed to insert these tokens on all sentences before training. To generate a sentence using period to define its end, we first initialize an empty string that will contain the sentence. Then, we loop until the model predicts a period. We get the next prediction of the model using the method .predict. The predict method returns an array with one element containing the predictions. We use the first position only because we will generate one character per step and use it to predict the next one. Since the model returns a vector with the size of the vocabulary, where each element has a probability of the next character to be that element, we get the one with higher value. Then we use the dictionary to transform the index to the corresponding character. Finally, we concatenate the next character on the sentence. After this, we need to update the variable x so that the next prediction will not be the same. To generate paragraphs or other kind of text blocks, you can just change the conditions of the while loop. One way to change the probability distribution over the vocabulary size is to use the scaling factor temperature. This name comes from physics, but all it does is to make the distribution smoother or not. It has positive values, and the closer to zero it gets, the model will emphasize the class with highest probability. This implies that the temperature will increase the probability of the class with higher probability and decrease the others. When the temperature is equal to 1, then there is no scaling on the Softmax function. For higher values of temperature, the model starts to use different words because it makes the probability distribution smoother. This means that the higher the value of temperature, the more equal the probabilities become. This leads to more creative outputs using words other than the expected one, but also leads to more mistakes. The temperature is a hyperparameter, meaning that you can try different values to see how it changes the predictions or leave it with the default value of 1. The scaling function is relatively simple. It has two parameters, softmax spread that contains the probability values returned by the softmax function on the last layer of the model, and temperature value defaulted to 1. It takes the logarithm of the softmax output and divides each element in the vector by the temperature value. Then it reapplies the exponential function. Next, divide the obtained values by the sum of them to obtain the scale distribution with sum equal to 1. The next step is to run one simulation of a multinomial distribution, using as probability of each class the values obtained in the previous step. Finally, we return the class that was obtained on the simulation of the multinomial, not necessarily the one with higher probability. You saw how cool it can be to generate text using RNN models, but you haven't actually seen the models. Let's fix that. The text generation models can be seen as a multi-class classification model, where the classes are each of the tokens in the vocabulary. As in the classification model, it uses a softmax activation function on the last layer, and uses categorical cross-entropy for the loss function. As an example model, we create a sequential model with two LSTM layers. We initialize the model class. Then add the first LSTM layer, defining the input shape with shape of characters window and vocabulary size. We also add dropout values to avoid overfitting and return sequences. Next, we add the second LSTM layer, adding the dropout values and not returning sequences. Then add the output layer with Softmax activation function. Finally, compile the model with categorical cross-entropy loss function. The model architecture is the same as in classification model, but the way we use the model is different. During training and testing, we don't compute performance metrics such as accuracy, because we are not interested in predicting exactly one specific sentence, but instead we want the model to be flexible and be able to generate sentences that make sense. To measure the performance, humans need to read the generated text and determine if they are good. If they are not good, we can train the model for more epochs or add complexity to the model by increasing the number of memory cells, adding more layers, etc. Also, depending on the task you are working on, it will be of interest to generate one character or word or sentence or paragraph, etc. So the output of the model is not the final result and needs to be further managed. Apart from generating text from TV shows characters or poetry, there are other applications for text generation. For example, it can create names such as baby names or new stars. Also, it is possible to generate marked text such as LaTeX, Markdown, or XML. Finally, it can create news articles or be used on chatbots. To prepare the data for text generation tasks, we need to transform text into sequence of indexes as usual. We will use characters as tokens for text generation. Then, we need to create the data for supervised learning, meaning that we keep a sequence of characters in X and the next character on Y. We pad the sequences in X to have the same length. This means that we will use the length of characters to predict the next one. The variable is called char's window. Y's dimension is the vocabulary size, or the total number of characters in the training data, and have to be one-hot encoded. In the previous lessons, you learned about text generation models. Now you will explore how to create machine translation models. As seen before, neural machine translation models are divided in two parts: the encoder that creates a language model for the input language and the decoder for the output language. Let's create an example encoder. We use the Sequential class for the model. Then we add the embedding layer that will create word vectors for the input language. The parameter mask0 inserts a 0 token for the vocabulary. Next, we add one LSTM layer with 128 units. The next step is to repeat the last state of the LSTM layer, the number of output language length, meaning that this will be used as input for the decoder part of the model. Note that repeat vector is a Keras layer not introduced before. Continuing right after the encoder, we add one LSTM layer that will return the sequences. Then we use time distributed together with dense layer to add one dense to each unit of the previous layer. This is useful when we are comparing the whole sentence instead of the final result like in classification. Keeping return sequences equal to false, the loss function is computed only in the last token, while keeping return sequences equal to true and using time-distributed layer, the loss function is applied in every token. This Keras layer is also newly introduced. When preparing the data, as before, we need to transform the text into a sequence of numerical indexes. We do that for both languages in the encoder and decoder part of the model. The encoder will transform the input language into a sequence of numerical indexes. The decoder, apart from transforming the text into a sequence of numerical indexes, it is also needed to one-hot encode each index to treat them as one class among the total vocabulary size of the output language. To prepare the input language, we first import the required objects, being the tokenizer class from keras.preprocessing.text module and the pad sequences function from keras.preprocessing.sequence module. Then we instantiate the tokenizer and fit the object on the input texts that are a list-like object containing the sentences in the input language. Then we transform the input sentences into sequence of numerical indexes by using the method text2sequences of the tokenizer. Finally, we pad the text by inserting 0 tokens to the right. The first step for the output language is the same as in the input language. We use the tokenizer and fit it on the output texts. Then we transform the output text and pad the sequences of numerical indexes. After transforming texts into sequences of numbers, we still need to one-hot encode each of the indexes. We create a temporary list, then we loop over each sentence of numerical indexes. We use the function toCategorical to transform each index in the sentence to the one-hot vector. The output language vocabulary size is the number of classes. Then we append it to the temporary list. After the loop is completed, we transform this temporary list into a NumPy array and reshape it to have 3 dimensions: number of sentences, sentence length, and output language's vocabulary size. To train the model, we just need to call the method fit and pass the training data contained on variables x and y. To evaluate a translation model, we can use the bilingual evaluation under study, or BLEU metric. This method is not in the scope of this course, and for details on it, check the NLTK documentation on submodule nltk.translate.BLEU-score. Congratulations! You came a long way to the universe of language models using Python and Keras. In this course, you learned 4 different applications of language models using Keras: sentiment classification, multi-class classification, text generation, and neural machine translation. Also, you learned the different types of sequence-to-sequence models. Finally, you learned the main modules and packages in Keras that make it possible to implement the models. You also learned about some pitfalls that occurs when implementing RNN modules, the vanishing and exploding gradient problems. To deal with those problems, you can use the GRU or LSTM cells. Also, you learned how to implement the embedding layer to create and/or use word vectors. Finally, you applied a few tuning techniques to improve the performance of the sentiment analysis model. When learning how to perform multi-class classification, you learned how to prepare the data, how to use trained word vectors for transfer learning, how to create the models in Keras, and how to access the model's performance. In text generation, you use characters as tokens and learned the necessary steps to transform the text into sequence of characters and next character arrays. Also, you created a function to generate sentences mimicking Sheldon from the Big Bang Theory. In neural machine translation, you used words as tokens, learned how to prepare the different languages' text data as encoder and decoder. Then you learned how to build a NMT model in Keras and used it to translate Portuguese small sentences into English. Again, Congratulations for finishing this course. I hope that you can use what you learned to other similar problems of your